Good morning, everybody. I hope you had a nice rest yesterday afternoon and you thought about the things that we've learned yesterday. It was a very, very, very interesting session yesterday. So we want to welcome you back to today and the session today. From yesterday, we have seen that really it is true that research helps to engage and helps us to know more. And we saw from Prof. Raymond's presentations yesterday that yes, he's more than 20 years of research in this area that definitely contribute to his knowledge, and now it's contributing to our knowledge. We want to thank Prof. Raymond for yesterday and for what he's doing today. And we also want to ask the people, please, if you want a question, put it in the chat. We want to have nice discussions after the presentations today. We've set aside quite a lot of time for discussions today in the program. So please, if you've got a question, put it in the chat or send Bertie an email. He will put the email address in the chat as well, that we can give it to Prof. Lister, but we can have those discussions afterwards. Remember, we also said you must look at some of your question papers. Maybe you can also ask some of those questions, because the more examples we do from this Bloom's taxonomy, the more we will know what to do. So please, we ask if you can put your questions into the chat. We want Prof. Lister to finish his presentation, and then only we will allow the questions. But thank you very much for all of you coming. I think this is a very good thing, not only for our universities, the teachers, and everybody that's taking part in this webinar. I really think it's going to contribute to the knowledge in programming and also into the knowledge of the 4IR in the future. Thank you very much, everybody, for your coming here, and thank you very much, Prof. Lister. Also, thank you very much for Bertie that's helping us with all the arrangements, etc. We really appreciate it. But we will, Bertie, if you want to give some other arrangements this morning, and then we will go over to Prof. Lister.
Thank you, Prof. Jovi. Thanks, everybody. So far, there's none. If anybody has a question that they feel that they don't want to post it in the open chat, you are more than welcome to email me. My email is available on the chat platform, Buitendag AAK, and then we will anonymize your question, and you're more than welcome to ask, and we will pose it to Prof. Lister. We will again, as last time, have a short questionnaire, and I beg everybody to, if you can, to please complete it for us. It provides us with some valuable information. I see a lot of people already has joined us, so we've passed the mic over to Prof. Lister, and we are sitting all with eager ears and eager eyes to learn more. Thanks, everybody.
Thank you, Bertie. And thank you, Joey, for that kind introduction. I hope today's talk lives up to the billing that you've just given it. I will briefly turn on my camera. There we go. Just so that I can say hello. I don't see, it'll hurt the bandwidth, I think, all the way from Australia if I leave it on. Besides, I don't think it's that attractive a picture, me in the corner there. So I shall turn it off again, having said hello. And I will go to the... Somebody saying something just then? No? Oh, hang on. And now I've got to... Oops. Got to...
Please remember, everybody, to mute yourself.
Yeah. And I think I'm sharing my screen. Is everybody seeing now a PowerPoint slide with a lovely picture of me and talk to at the top of the page? Is that what you're seeing?
Yes.
30 or, yep. Good. Joey, that's it. That's what you see. Excellent. Okay. I won't say much again. This was a slide from actually yesterday. And as has already been mentioned, I taught for about 25 years. recently retired, and yesterday's talk was a sort of a development of my early stages of teaching, and then in the very early stages of research in those years. The reason for doing it as a chronological introduction to how I developed is I think it's actually quite a way for anybody to sort of go through the steps of thinking about this stuff. So today is really the period from about 2004 to 2009, and by the end of this period, I was quite the education research evangelist, as I think you'll discover as we go along. And I think, as I said yesterday, my first few years, of course, I didn't do any research at all. I just taught the way most people do, which is really by your own intuitions and feelings about things. And I think that part of the problem with that is that you can end up doing what I call a random walk in pedagogical space. You get to the end of the semester, and some of you, quite a few of you, have just arrived at the end of the semester. You've marked your exam papers, and you're sitting there thinking, "Oh dear, there are some students who really didn't learn all sorts of things. So maybe I should change something next semester." And here's a curious thing: often, if you think about it, if you introspect on this, we see that the students do badly on the paper, and then we say to ourselves, "I wonder what change would improve things," and we make that change. It's not the exam, the data we see in the exam itself. It's the overall marks. The students do poorly. We tend not to make deductions about where the problems are from a close examination of the exam paper or any other assessment item. It tends to be a gut feeling about what might not be working, and we take that to the next semester. And sometimes often our intuitions are very good, but in general, I'd have to say that they are, in the greater scheme of things, changes of direction in a random walk in pedagogical space. Now, maybe I shouldn't bore you with this slide because maybe it's just too personal. But what I'm showing you here, obviously, is a page from Amazon, and on it is a very old textbook, A Guide to Fortran 4 Programming, written by a fellow called Dan McCracken. By the way, I talked a lot about a fellow called Mike McCracken yesterday. Just for the record, Dan McCracken and Mike McCracken are not related. Mike was very insulted one day when I asked him if they were, because Dan McCracken apparently is a great deal older than Mike. And this is a book of great in personal significance, because I started my university career as a first-year student in 1978, just yesterday, 1978. And this was our textbook for learning to program in Fortran. And of course, as things went in those days, it was Fortran, and we wrote it on punch cards, which we put through a card reader. Such a disappointing thing that card readers have gone away. If you've ever seen an old-fashioned card reader reading dozens of cards every second, it's quite a sight. And then, the cards were read, and your Fortran program was sent to the university computer, just the one in the whole university. And if you were lucky, a run came back the next day, and you got to see how badly your program worked. That's how things were back in 1978. But here's the thing, I actually went into Amazon and I bought my old textbook. Back in 1979, I probably sold my original textbook to the incoming class, somebody in the incoming class. I didn't have it. So decades later, I bought my old textbook again, and I opened it up, and you'll have to take my word for this, I guess. I opened it up, and as I read through it, and this was a year after I'd been teaching myself for years, I said to myself, really, the way we teach programming hasn't changed. Now, obviously, we weren't teaching Fortran anymore, and we weren't doing it on punch cards, and we certainly weren't doing it on the university computer. We had labs full of 30 machines a lab, and half a dozen labs probably. But when I looked through the book, I thought the pedagogy for teaching programming really hadn't changed since I'd been taught programming in 1978. There'd be a little section on this is how you declare a variable, and this is what you can put an integer value into this variable and a real value and so on, and then there'd be some exercises. Now that we've told you that, write some code. And then, a week or two later, there'd be if statements, and this is how an if statement works. And now that we've shown you, here are some exercises, go away and write some code, and so on. Loops. This is how the loop works. Now that we've shown you, go away, write some code. And here's the thing: the pedagogy hasn't changed. I will make that assertion. None of you probably were learning programming in 1978, so you'll have to take my word for it, that things haven't changed that much in the pedagogy. I mean, here we are. I programmed on punch cards. and ran my program on the university computer. And here we are decades later with web services like Amazon. The world around us has changed so much since 1978. But I will maintain that the pedagogy, the most common ways that we teach programming, have not changed at all, really. The language has changed, sure, but apart from the translation from one language to the next, the textbooks themselves haven't changed. The pedagogy hasn't changed. And I thought a lot about that for quite some time. High school students, the intending high school teachers, please bear with me when I talk about academics for a moment. I maintain what we lead a rather strange double life. If I can get that slide to come back up again now. There we go. In our research lives, in the left-hand column here, we read other people's papers. We go to conferences and seminars and listen to them speak about their research, and then we go away and do our own research. And probably we live in a community where there are theoretical and empirical frameworks for how we should do good work, and if our work's good enough, it gets accepted for publication. And then we go to the conference or whatever, and we present, and other people learn from us, and we go round and round and round this cycle. And that's why we've gone from punch cards running on the university computer in 1978 to Amazon and Google and all sorts of other great things, Microsoft Teams, I suppose, decades later, because we progress. Research progresses and spills out into industry and so on. That's one of our lives. But the other life, the teaching life for an academic, is so different. For the most part, it's an introspective life where, we teach our class, and then we sort of think about it. About this time of year, you start thinking about what worked and what didn't work in the previous semester, and you might make a few changes and so on. But it's a relatively private process. You may talk to some colleagues in your own institution, but you're unlikely to get on an aeroplane and go internationally and go to a conference to find out how other people are teaching. And also we work within what are called folk pedagogies. This is a term coined by Jerome Bruner, I think, back in the 90s. And it's a very fancy way of saying you work within personal intuitions about how people learn the particular subject. You don't really work within well-defined theoretical and empirical frameworks. And finally, the outcomes remain relatively private. Sometimes it's good they remain relatively private because sometimes the outcomes are not great. Maybe your class did very badly and you prefer not to talk about it too much. So there is and of course, as I say here, the feedback loop is the most important part in research. We build upon each other's work, but there's no real feedback loop. You might talk to a few like-minded colleagues, but in general, there's not a big, rich feedback process in our community. As I like to summarize it, in research, we progress and we go from punch cards on the university computer to Amazon and Microsoft Teams. We progress over the decades because we keep building upon the work of other people. As Newton said, if I've seen further than anyone else, it's because I've stood upon the shoulders of giants. By the way, a short digression on that, if you've ever heard that. It sounds very noble that Isaac Newton said that, doesn't it? If I've seen further than other people, it's because I've stood on the shoulders of giants. It turns out that it's widely speculated the reason why he said that was because one of his great rivals was Robert Hooke, and Robert Hooke was a very short man. I digress. We build upon research cycles. Whereas in our teaching lives, I think we're guilty of sort of perpetually reinventing the wheel, or if you prefer, a random walk in pedagogical space. There's no reason it has to be like that. There's no reason why we can't approach teaching more like research. Now, those of you who simply say to yourself, I don't want to do research, fine. Just bear with me for a moment and I'll try to persuade you that I'm not really talking about building large hadron colliders and placing students inside them and bombarding them with W and Z particles to find out something about them. I'm talking about something more modest than that, and I'm talking about a mentality more than highfalutin, high-financed, big grant money research. There certainly are computing education journals and conferences where you can read about what other people have done, and there are well-defined theories about how people learn, such as constructivism. I think these days we're all kind of constructivists, if we've heard that term. And certainly yesterday we talked about Bloom's taxonomy a lot, and I suspect we'll talk about it some more today. Cognitive load, you name it. There's lots of well-defined theoretical and empirical frameworks. And of course, you can publish. I mean, if there exist computing education journals and conferences, there's no reason why you can't write papers and then publish them and people can learn from you. We can have that feedback loop and we can build upon the work of other people. It's just that currently we tend not to. Now, some of you might be thinking to yourself, I'm a teacher, I don't want to research. Some of you, I know, being educated to become high school teachers, so you're not thinking of yourself as a researcher. And some of you might be working in universities that are more focused on teaching rather than research. And I congratulate your university on that. That's a noble pursuit. I'm not being condescending at all about this. But I believe that if you just bring a little bit of a research mentality to your teaching will work better and you'll be happier with your teaching. I mean, as it is, you try out new ways of teaching things every semester. And there's no reason then why, you can't say, look at your exam results and satisfy yourself that what you did worked or did not work. And then, of course, here's a little slogan that I'm going to keep showing up as time goes on. A good exam should teach you something new about your students. I mean, we think of exams as a way of putting numbers to students, putting a grade or a mark out of 100 against a student's name. And certainly, I guess it's fair to say that is the primary goal of any exam or any other assessment item. But a good exam should do more than that. A good exam should teach you something you didn't already know about your students. My students can do this, but they can't do that. And then it gets you thinking in a very productive way about what sort of changes you'd make, rather than just looking at the overall grade distribution at the end of the semester and saying, gee, the students did poorly again this semester. What might I change? You actually go into the exam paper and you examine question by question how the students are doing, and in particular compare student performance again on pairs of questions. The students could do this question really well, but for some reason they can't do this other one. What am I missing here? So be guided by the results in your exam paper, and of course that informs how you go about teaching the following semester. And that is essentially, if you get in seriously and examine what you can learn from your assessment materials, and particularly your exam, that's really all I'm saying is a research mentality. Perhaps you don't want to fly internationally and present your results at an international conference, fine. But that's not really necessary. You do need to talk to people. You can't do research all by yourself. Well, you can, but it won't be in the long run very good. You need to bounce your ideas off other people. You need to hear other people's ideas. Research is a social process. But, your research community doesn't have to be some highfalutin international body. It could be something quite simple like a like-minded group of people who meet and share in a pub once a month. Try to pick a pub that's not too loud, because you do need to talk and be able to hear each other if you are going to do this in a pub. Now, but if you do meet once a month in a pub, try to be research-oriented in your conversations. And what I mean by that is it's easy for a group of people talking about teaching to stop being a research group and to become what I would call, perhaps melodramatically, and I mean no offense by this, a religious group. And what I mean by that is people hold to themselves very dear beliefs about how teaching should be done. And they argue about it, but nothing ever comes of it, because there's no way of deciding who's right and who's wrong. It might be a religious group in the sense of, you can imagine you might have a Buddhist and a Christian meeting in a pub once a month, and they debate each month who has the better religion. And of course, neither of them changes their position. There's no going forward. And that might be entirely appropriate for a religious group, but that's not appropriate if you're trying to improve teaching through a research mentality. You've got to solve your disagreements by saying, well, how could we, demonstrate this? For example, suppose somebody comes to one of your monthly meetings and says, I believe that students learn better when they're in a classroom where the walls are painted green. Now, right now, you're thinking, well, that's a silly thing, but I can tell you that in my old university, UTS, there is a lecture theatre that's painted green precisely because somebody high up in the university administration believes that people learn better in green rooms. Don't share that with anybody from my university, by the way. But, you could sit in the pub and have a very entertaining hour or so over a few beers where that person says, green walls mean students work better. And you say, no, don't be silly, it can't be. And they say, no, it's true. And you say, no, it's not. And you go, yes, no, yes, no, yes, no for the full hour. And you're not getting anywhere. You need to collect data in some way to solve that. That's kind of, you might remember my two dogs from yesterday. Here they are again. This is what you've got to try to avoid. There are a lot of 90% of your teaching might remain intuition, and that's all right. But when in that other 10%, there might be things that can be proven to be correct or incorrect by doing research. And when that's possible, there's no point in just arguing about who has the better intuition or who learnt. You've got to try and solve it with data. And as Nietzsche said, convictions are more dangerous enemies of truth than lies. Right. This is a lot of writing on one slide, isn't it? I might pause for a moment and just let you read it. By the way, here's a teaching tip, a very small one, but it's sometimes I pause in lectures and have the students read a bunch of stuff on a slide like this. It helps to wake up the students who've fallen asleep while they've been listening to my droning voice. And a little teaching tip, I always read through the material on the slide twice to myself quietly to give the students enough time to read it once. Now, I won't talk about the stuff in the big font for a second. I'll go to the thing. One of the things near the bottom, not just a constant source of disappointment. Given that I know that many of you have just finished marking exam papers, you probably are feeling a bit disappointed about how the students went. And when you don't have a research mentality, it's just, well, what will I try next semester? It's just, this is terribly disappointing. What might I change and hope that things get better? Whereas if you approach the exam paper with just a research mentality, it becomes a much more constructive process. If you learn something new about your students, although it might be disappointing that they did, if you learn something new about from your students from the current exam, then you go to next semester feeling more confident that things will work better next time. And that's just a much happier way to live, honestly. I'll leave you to read this one as well. This was a quote that I found very early on when I was making my transition to be an education researcher, and it was pivotal for me. I had this stuck above my office desk for several years. Right, I've read through it twice. I have nothing more to say other than that I found it an inspirational quote which I stuck above my desk, and maybe some of you might do the same. So what I'm going to talk about now for a while is my 4 trips around this cycle of approaching teaching as with a research mentality, and show you how my thinking about teaching changed as time went on. We've actually already been through one of them, and that is how the stuff I talked about yesterday. So my first trip around this cycle will be relatively quick. It'll be revision from yesterday. And in fact, I won't do the 4th cycle until tomorrow, so probably won't. So we're really only going to go twice in detail around this cycle today, your time. Okay, so my starting point, this is revision from yesterday. My first time that I really approached things as a researcher was when I read the McCracken paper. I became aware of it, which came out in 2001. I just want to remind you of the McCracken paper very quickly. We went through this in gory detail yesterday, so I will be fast. My apologies to anybody who missed yesterday's talk, but because of the people who did hear it, I don't want to spend a lot of time on this one. So they put students in a lab for 90 minutes, and they collected data at 2 universities in the US and 2 in the UK. The students handed in what they'd produced in 90 minutes from their computers, and then they graded what the students handed in, and many students did badly. And as I'll remind you what the bar means here, you got to mark higher. You were on this side of the line if you handed in something that compiled and it bore some resemblance, however modestly, to what the to the problem you were supposed to solve. So everybody over here, and there's a lot of students, handed in something that either didn't compile or bore no resemblance whatsoever to the problem they were being asked to solve. So the students did very badly. And McCracken's conclusion, Mike McCracken, the first author of this study, conclusion was that the students couldn't problem solve. They couldn't start with an informal description of the problem. That's what the students were given, a short written description of what the program should do. And they couldn't sort of think about the design of the program, break it up into some modules, write the modules, put it all together, and then run the code and see that it wasn't working, and then debug their code and so on. And that's what he referred to as problem solving. Problem solving is a term that's been around for a long time, and it means different things to different people, but that's what Mike McCracken meant by it. When I read the McCracken paper, I said to myself, now that I was starting to adopt a research mentality, was, well, didn't those famous scientists like Einstein and someone say that, the best theory is the simplest theory. Theory should be as simple as possible, but no simpler. And I said to myself, that's a very bold claim that students have a very high level problem like that. I mean, maybe they have much more modest problems than that. And as I facetiously said yesterday, maybe they couldn't read the language in which the question was specified to them. That's facetious, but that would be a problem. So that led me to lead my own research group in which we called the Leeds Group, in which we met in 2004 in Leeds. That's why it's called the Leeds Group. 12 universities in 7 countries. We collected data in all 12 of the universities in all of those countries, more than 500 students. We collected data from more than 500 students. And this is the sort of problems that we gave the students. One of them was a tracing problem like this, which is, you give them some code and then you say what values in a certain variable after the code is executed. I think we gave 12 multiple choice questions to students, and this was 7 of the 12 were of this frame of mind. Oh, and I did this little calculation yesterday for you. What's the probability of guessing this correct answer to this multiple choice question? Well, there are 4 options, so the options are, it's 1 in 4. So what's the most likely score if you guess all 12 multiple choice questions? Well, there's 12 times a quarter, which is 3. And so then we move to how the students went on the 12 multiple choice questions. Well, a quarter of them, the top 25%, scored 10, 11, or 12 out of 12. Great. That's pretty good. Tracing is an error-prone activity. I'm not too worried if they got a couple wrong with simple errors. A little bit more worried about these guys, but, I'm not going to spend a lot of time worrying about them because I'm more worried about the other half of the class, the bottom half. I think people who are scoring roughly 6 out of 12, 5, 6 or 7 out of 12, that means they're getting every second question wrong. And that says to me that their tracing skills and so on are very poor. And how are they going to debug their own code if they can't trace it? Let me say that again. I think it's a simple question, but it's one really worth thinking hard about. How are your students going to debug their programs if they can't trace their own code? And then finally, as depressing as it is with the students in the third quartile, the bottom 25% were performing at a level consistent with chance. In fact, probably students who scored 5, maybe even 6, were performing at level, were effectively guessing all the questions. They just got a bit lucky. Some students who guessed were less lucky and scored lower than 4. But, 3 or 4, a lot of students, 25% or more, were performing at a level consistent with chance. Now, if your tracing ability is at a skill level where, it's basically down to chance whether you can get the right answer, you don't have the skills to write code. So I reject the McCracken explanation. Now, there may be students who can't problem solve, who have that high-level problem that McCracken talked about, but an awful lot of the students haven't got to that problem yet. They're still trying to figure out how code works. So my first take-home message as a teacher to you, by the way, is you should be explicitly teaching and testing tracing. We tend not to. We might, when introducing a while loop, we might go through that code and how a while loop works. We might demonstrate how a while loop works by working through one, by tracing the numbers on the, out the front of the lecture theatre. But we rarely then get the students to do to get a tracing exercise, and especially rarely do we check to see whether the students could trace by having some sort of a test at some point. It doesn't have to be at the end of semester, which is a bit late. It could be, much earlier in semester. Tracing is a foundation skill. It's the skill upon which I will maintain as tonight and tomorrow goes along. It's the skill upon which all programming ability is built. I still bump into people who want to debate with me whether tracing has any relevance to people writing code. And I think rather than me saying, yes, it does, tracing is relevant, and them saying, no, it doesn't, yes, it does, no, it doesn't, I think I'm going to try and present data during this talk to persuade you that tracing is very relevant to how students learn to program. So there's your first take-home message. As a teacher, it came out of my research, but there it is, explicitly teach and test tracing, especially test the tracing skill. Establish that they can test, that they can trace. And remember this, because apart from the fact that it might be useful in your teaching, this will be on the test. This message, there'll be a question. There'll be a question where you have to tell me what the first take-home message was. Okay, but you might be overthinking it at this point. Am I suggesting, let's go back, but am I suggesting that we give students problem after problem after problem like this one and have them, trace through the code, and we don't let them write code? Well, that would be a recipe for getting a lot of students to drop out of your class, because they would be bored so badly if you just did tracing after tracing after tracing. You've got to be smart about this and turn it into something that feels like a productive exercise to them. And that's part of the skill of a teacher. I'm not going to offer you up a research conclusion on how to make tracing interesting. I haven't done research on that. It's just as one teacher to another, I'll say to you, you've got to teach tracing and you've got to test the students on it, but you've also got to make it interesting to them in some way. So getting back to where I was, implies we should teach tracing before code running. Well, yeah, if you look at your own slides on how you teach program right now, you probably have, for say, if you're teaching a while loop, you probably do have one tracing exercise where you illustrate how the while loop works. Then you probably very quickly move on to thinking about how while loops work in more abstract terms, but at least you initially presented it as a tracing with a tracing exercise. All I'm saying is that you need to get the students to do some of those. Furthermore, you don't necessarily have to teach it before. Well, not a lot. I recommend doing a little bit of tracing before you ask them to write. But really, the most productive situation where a student can trace code is when there's a bug in their own code. And then they learn the utility of tracing when there's a bug in their own code. I mean, I'm sure that you've had students come to you, to your office and say, I can't get this code to work. What's wrong with it? And you look at it, and within seconds, it's pretty obvious to you what's wrong with it. But the student hasn't traced it, possibly because the student doesn't know how to trace. So it can be very effective when that student comes to you and says, I can't get this program to work, a good thing to say to them is, well, have you traced the code? If they haven't, well, okay, here's a teaching moment. You could tell them, and this is up to you as a teacher, you can tell them to go away and come back when they've done a trace. Or you could say, let's sit down and do some tracing. Let's put some values in and see where this program goes. And actually, you get them to try and do the trace. And as they work through, you get to see whether they can trace or not. And you might find that your intervention with a student in your office is not really about them getting that piece of code to work. Your intervention is really about improving their tracing skill. And this is what I mean by, you can also think of tracing as a diagnostic and a remedial tool. It used to be the case, I'd look over a student's shoulder in a lab and I'd see them writing code and it was, it wasn't working. And, what do you do with that sort of student in that moment? There can be all sorts of reasons why the student is struggling to get their piece of code working. And I suggest, often the first thing to do is to say to them, look, well, let's trace your code. Let's put some values in and see if you can figure out what's going on with it from that. And then you can establish whether the student can trace or whether they can't. And then well, if they can't trace their own code, I need to get them improve their tracing skill. And if they can trace their code, then the problem is a more sophisticated problem. Maybe they have Mike McCracken's problem they can't problem solve. And you move on to helping the student that way. Well, it would be if you gave them problem after problem like that. But let me give you a couple of examples. Teaching, this is from a paper I saw in 2016, teaching computer image processing subject to middle school students. Middle school is an American term, isn't it? I'm not entirely sure what middle school means, but I think it's kind of the early teenage years, something like that. 13, 14, something like that. 15 maybe. So this particular person was teaching the students some I assume, elementary image processing, given that they're in middle school. And there was a little quote in the paper that I liked very much. The students practice manually by hand worksheet and then do the exercise on the computer. In other words, they trace the code. Well, if they didn't literally trace the code, at least they traced the algorithm. That's possibly the sort of thing that you need to think about, doing something interesting like that. Doesn't have to be image processing. For those of you who are going to be teaching, particularly those of you, if there's anyone who's going to be teaching in primary schools, I think there's tremendous scope for interesting tracing exercises for detaining children. For example, you could have a maze. You could present the students with a maze, put it up on the blackboard or whatever, and have the students write their programs. By the way, I really enjoyed yesterday's presentation by the other speaker, where you had those things running on the mobile phones. That was just fantastic. Really just wonderful work. And what I'm saying could apply here, I suppose, kind of, except I'm suggesting that you truly do it offline. He was doing it on the mobile phone. I guess I'm suggesting this is an entirely offline process where, or non-computer based, non-mobile phone based, because you present the students with the maze and then you get them to write down, possibly on a piece of paper, their algorithm for, their series of instructions to the computer on how it works its way through the maze. And then you ask them as a class exercise to hand simulate the exercise. That is, by walking around a maze, put something down on the floor and have the students walk around it. And I think you can get some lovely classroom activities going that way. For example, somebody might start executing their own code, and then and you presumably have a copy of their code so you can see what they're doing, and everybody should be able to see what they're doing, and they actually start to correctly walk around the maze, but in fact that what they're doing in that moment on the maze is not what their program says they should do. So you have this wonderful moment, you go, hang on, what did you just do? Is that what your code says you should do? That's just tracing. You might have students swap, one student writes the algorithm and another student then becomes the robot and walks through. And again, that student might be tempted to do the correct thing and not follow the code. So you can have, look, I'm going to stop at this point, because as a researcher, I don't think that I have half the ideas that lots of teachers have about how to make their stuff entertaining. You can make tracing entertaining. Okay. Now I'm going to get back more into a little bit of a research mode, and talk about one of the mysteries that we had in the data from the multinational study from 2004. Something we didn't understand, because we did more than just simply mark the multiple choice questions as right or wrong and then present that table that I showed you a moment ago. We had collected other sorts of data. And one of those sorts of data was think aloud. You might remember there were 12 people in the group, in the Leeds working group. Each of us had to not just get our class of students to do the 12 multiple choice questions. We had to find 3 students. Each of us had to find 3 students, and we had to sit with that student while they did all 12 questions. And we had to instruct the student to think aloud as they did it. Tell us what they were thinking as they were attempting the problem. And 12 of us, 3 students each, so that's 36 students that we collected think aloud data from. Okay, so here is one of the questions that we gave the students. Question 4. Now, I don't suggest that you read all this code, especially those of you who are watching this on a small screen. It will be too small. I just want you to focus upon the code for a moment in this rectangle here, and to actually help you, if you are looking on a small screen, I'm going to blow up that into something bigger. That code that I'm showing is inside a while loop. You can see there are 2 arrays, x1 and x2. You'll see we do a test, we do an if condition, and if the if condition is true, we increment a variable called count. And I'm going to give you a further hint so that you don't have to read all the code. What I'm showing you there is the only place in the code where the variable count is being incremented. Now, clearly, if I said to you, what's this code doing? Explain in plain English what this code is doing. It's counting something. That's why you have a variable called count. So would anyone, well, if we were in a room, let me say at this point, I would stop and I'd force somebody in the room to tell me, to make a guess on the basis of just that little bit of code they're looking at, what the code as a whole is doing. And I'm not going to try and do that now because I haven't perfected the art of doing that in a Microsoft Teams or a Zoom environment. I will just tell you the answer. A good guess would be, well, I guess it's from what that little bit of code you're showing me. I haven't read all of it, but from that little bit of code you're showing me, a good guess would be it's counting the number of elements in the two arrays, X1 and X2, that are equal. And that's a pretty good guess. It doesn't quite handle all the cases where there are multiple occurrences of the same value, but let's not worry about that. That's a level of detail we don't need today. Let me put it this way. When I present that code on the right-hand side on a piece of paper to colleagues, and I have done this, we've written a paper about this, we give experienced programmers, academic colleagues, all this code, and we say to them, we give them this whole question, all this code, then we say, after this code is executed, what does it do? And you watch the academics and they go, well, let's see, there's a while loop. Yeah, okay, righto. And they say, oh, it looks to me like it might be counting equal values. And then they have a little bit of a look at the rest of the code. It's slightly more complicated than that, but let's not worry about it. Let's just pretend for a moment it's counting the equal values and leave it at that. And then what do? They go up to the array and they don't trace their way through the code. They don't play human computer and execute all this code. They go up to the data and they just count out the number of equal elements. I'm not sure what count ends up being because you've got two twos this one, but because you're incrementing I2 once here. So when we get to 2 and 2 here, we'd stay on that 2, but we'd move this one along, so we'd count twice. The 2s would be counted twice. So let's see. So there's 2 1s, so there's one occasion. There's 2 2s, so that's 1 2. And there's 3. I feel like the answer is D. Okay, you see how I just did it? We knew what the code does. We then went straight to the data and we didn't bother looking at the code. But here was one of the mysteries in the Think Aloud data. When we asked 36 students to solve this problem, they didn't solve it that way at all. Students worked out the answer by tracing through the loop multiple times. They just played human computer. They went crank, 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 crank through the code. As we said, and this is a quote from the paper, none of these students volunteered any realization of the intent of the code to count the number of identical elements in the 2 arrays. Whereas practically every academic we asked to do it did what I just said. They first read a bit of the code. They said, oh, well, I think it's counting, equal values. So the academics very quickly, experienced programmers very quickly deduced what the meaning of the code was, what it was doing, and then just jumped straight to figuring out the answer. The students, on the other hand, at the end of their first semester of learning to program, did not do that. They cranked their way through it. They went through this loop. So you would have gone through this loop, let's see, once, let's see, that one gets incremented twice, then 3 times, 4 times, 5 times, about 6 times, 6 or 7 times. They just cranked their way through it. And at no point did they even stop halfway. They're just like, oh, now I see what it's doing. They just cranked their way through it. And we summarize this as, oh, by the way, this was the same. This wasn't just a peculiarity of question 4. It was what happened for all the tracing questions. There were 7 out of the 12 questions were tracing, and this is what they did for all of them. And as we like to say, the academics deduced what the code did. They saw the forest. But the students didn't. The students saw the trees, the individual lines, and they traced their way through them, but they did not see the forest. So, this is back to me evangelizing about the importance of tracing. By this stage, we're talking about 2004. I'd been teaching for about 10 years at this point. Now, I'd never realized that sort of thing was going on with my students. I'd always assumed that, if I had a piece of code like this, I assumed the students did it the way that, I just described. Oh, it's probably counting identical elements and so on. I never realized that the students were doing it a different way. And that's because when you're teaching, you're so busy teaching, you don't sort of step back and take a look at what's going on. And let me put it another way. A student comes to you with a problem. I can't get my code to work. Your job as a teacher at that moment is to focus on helping that student. And, if they start doing something and they start doing it wrong, you stop them immediately and you get them to, you fix, no, don't do it that way, do it this way. So by the very act of teaching, you intervene and you stop the natural behaviour of the student, which is probably a good thing from a teaching point of view. You want to change their natural behaviour. But from a researcher's point of view, you don't want to intervene and stop the student from doing what they're doing. You want to leave them to do what they would naturally do, and you want to watch and think about what they're doing. And that's the difference between being a teacher and being a researcher. Sometimes as a researcher, you need to step back, not intervene, and just watch what the students are doing and think about it. Like I said, it took me 10 years to realize that. So that was my first trip around the cycle. Oh, yeah. Okay. So, yes, this was my first trip around the cycle. We had the McCracken study. Now, was there any theory involved? You know, over here in the research thing, we say there should be some sort of a theoretical or empirical framework. No, there's no theory at this point. It is very immature stage of development of my understanding of how students program. Was there an empirical method? Well, you know, if giving students 12 multiple choice questions and then getting 36 of them to think out loud and so on, if that's an empirical method, okay, good. It's pretty modest by the standards of research, but it's, you know, it was effective. We have argued in past papers that, in fact, the real innovation from a research point of view here was to combine data across multiple universities. Because if you did just study at your own university and then try to publish it, and published it, the audience members would just say, oh, yeah, that might be true of your students, but it's not true of mine. So in some sense, collaborating across multiple institutions was an innovation. And, of course, we published. So there's one iteration around the loop. And then, of course, here comes my second iteration around this loop. And that took me so long to get that piece of graphic to going. I'm going to show it again. Look at that. Look upon my works, ye mighty, and despair. No, look upon my PowerPoint, ye mighty, and despair. Okay, so let's go around the second trip. So we've just finished the multinational study where we've got students to trace code and so on. And we've got this mystery. Our research the second time around is informed by this thing that we saw in the initial experiment that we didn't understand. We knew that the academics abstracted from the code to what it was doing and then solved the problem that way, but the students weren't doing that. So what's going on? The second time around. Let's watch it again. So here we go, the second time around the loop. And this is what's known as the bracelet study. It was a 6-year collaboration amongst 7-year collaboration where we studied this sort of thing. In the end, we wrote over 20 papers, 26 authors, 40 institutions, 7 different countries, which sounds huge, but in fact, it started very modestly. Tony Clear from the Auckland University of Technology. Here in Australia, we refer to the Tasman Sea between Australia and New Zealand as the pond. And so Tony on the other side of the pond said, I like that stuff you did in the multinational study. Why don't you come over and talk to us about it? And so I went over and gave a seminar, and Tony invited a few people from universities in the Auckland area. And that's how we started, really. It was just a bunch of people who got together. And we did go to the pub after I'd given a seminar, and we continued to talk about teaching at the pub. So it had very modest beginnings. It grew into something over multiple years, much grander, but it had very modest beginnings. Just a bunch of like-minded people meeting regularly and discussing things they were seeing in their exam papers. So this is where we kind of started in the bracelet study. We said, well, I think Lister et al. 2004 establishes that a lot of students have problems tracing. McCracken maintained that students had problems with, writing and designing their own code, and we don't deny that there are students who do, but there are students with much more mundane problems. And I think the question that the Lister et al. 2004 begged to be asked was asked by the Bracelet Project, which was, is there anything else in between? Are there other places, other levels that students pass through on the way through? Okay, so that was our research question, if you like. Simple question. Can students see the forest, not just the trees, or do they have to be able to see the forest in order to be able to write code? And what was our tool? We sat around in a room and we discussed how would we go about investigating that. And after a lot of discussion and throwing away a lot of ideas, somebody suggested, and it wasn't me, somebody suggested a very simple idea. They said, look, if we want to test whether students can understand a piece of code, if we You're going to give them pieces of code like this. Instead of just always asking them to tell us what values in a variable count, why don't we just ask them what the code does to see if they can do that? And that's what we did. Sorry for the tripping around. That's what we did. We invented what we called the explain in plain English question. So we give the students an instruction like this, in plain English, explain what the following code does, and then we give them some code. And then we'd ask them, well, and by the way, I'm trying to fit this on a single overhead. There are all sorts of problems with this as a well-crafted question. For example, the students might think from this instruction that we want them to give them a line-by-line description of what the code does. That's not what we wanted. We want an overall summary of what the code does. So clearly, as an exam question, there's some craft work to be done in this question turned into a good question. I'm just trying to make it fit on one slide, so that's why it's ambiguously phrased here. So we've got this array called iNumbers, and we've got some suitably one of the problems with these sort of exercises that people don't like is you've really got to use meaningless variable names. If you're going to ask people to explain what the code does, you can't effectively tell them the answer by giving them a meaningful variable name. You've got to disguise what the code does by giving meaningless names. But so we've got this thing called bValid, which we set to true, and then we have a for loop which runs through the array, and then we have this if condition. So we compare two consecutive elements in the array, and if the first one is greater than the second one, we set the flag to be false. So if we were sitting in a seminar room, at this point I would stop and I would insist that somebody in the room tell me the answer, and usually there was a long silence, and then I would say to them, you remember all those times in your lecture theatre when you're throwing a question out to the students and none of them answer? And you remember how frustrated you are that the students won't answer? Well, here's your chance to show that you're not like that, at which point somebody does volunteer an answer. Everyone's worried that I'm looking for a really complicated answer. I'm not. I'm looking for quite a simple answer. And the answer is it checks to see if the array is sorted. Now, some of you might say, yeah, but hang on. What if there are identical elements in the array? And do you mean sorted ascending order or descending order? By the way, I think it is descending order, but that doesn't matter. If a student answered, it checks to see if the array is sorted. I'm happy. That's a wonderful answer as far as I'm concerned. It might not be absolutely perfect, but it's sufficiently good for my purposes. As far as I'm concerned, a student who says that can see the forest. They may not be seeing all the details of the forest, but they're seeing the forest. Now, the second problem we were very pleased with ourselves. We invented this type of question. We all went back to our respective institutions and inserted this question into our exams to see what the students would do with it. Then we had a problem. How do we analyze that data? Oh, by the way, before we get there, while we're at it, since we've talked about Bloom a lot, I would classify this to be an analysis level question. In plain English, what does the code do? It's small enough to be analysis, the code. Yeah. Right. And so we hit upon using what's called the Solo Taxonomy, something developed by a couple of guys called Biggs and Collis in 1982. And what they took, it's another taxonomy, like different from Bloom, but another taxonomy. And what they said was that we can analyze this data in terms of, we can put a student's answer into 4 categories. At the bottom is what we call the pre-structural. So pre is the operative part here. The student can't explain the code at all. And the most common pre-structural answer is a completely blank answer. The student just didn't give an answer at all. And if you want to understand what pre-structural means, if I wanted to give you a fairly solid definition, I'd say, imagine you gave this question to the students, you gave them this code before they started your course, your subject. So they know nothing about programming. Well, yeah. What sort of an answer could they give you? That would be a pre-structural answer. Next up is Unistructural, which means that they went to at least some of your lectures and they learnt some of the material that you gave them, and so they can explain some of the lines of the code. They can't explain the whole thing, but they can explain some lines of the code. Like, I don't know, this line sets a variable called bValid to be true. This line creates an array. Tell you some of those lines. So the operative part here is unistructural. Uni, of course, means one, but we don't literally mean they can only do one line. Let's just say they can explain less than half the lines. I'm not too worried about exactly how many lines they can, but they can't explain most of it. Now, what you might suspect when we step up to the next category, multistructural, is Yes, they can see multiple lines. They can see the trees. They can tell me, and some of them do, give me an absolutely completely correct line by line description about what that code does. They don't take the extra step telling me what the code as a whole does. Some of you might say, well, you know, your explanation was ambiguous. Yeah, your instruction to the students. Yes, there's a lot of experimental method I'm glossing over here to make sure the student understands that you want them to give you a summary of the overall code. I'm skipping over that for the purposes of this talk. And so multi, I mean, maybe they can't explain every single line, but they can explain most of them. Then finally, the most interesting category, the one that we really want the students to do, is the relational category, where they see the forest, they see the whole thing, and they say, oh, it checks to see if the array is sorted, or something like that. Explain pithily what the code does as a whole. In fact, if that was too much information, the Solo Taxonomy in its entirety, don't worry about pre-structural, unistructural, and multi-structural. Don't stress too much about that. That's really the sort of answer we're interested in, relational. There's, you know, it's Sydney or the bush is an expression in Australia. You probably have similar expressions in, so it's in New Zealand, it's Auckland or the rest of the country. It's relational or it's not relational. That's what we're really interested in. So here was our experimental method. I guess what I haven't said is, hello, is that a deliberate intervention or is that somebody just accidentally turning the microphone on?
It's an accident.
It's an accident. We shall keep going. I think we'll have a break shortly if people are getting tired, but let's persist until we at least get through this iteration of the research cycle. What's implicit here, what I should have put in this slide is when I say give them some students, we gave them some questions in their end of semester exam. One of the beautiful things about giving the questions in the end of this, well, there are several beautiful things about giving them questions at the end of semester exam is it's just, you've got to run the exam anyway. So you're not making extra work for yourself. Secondly, the students have got to do them. You know, if you're asking students to volunteer to answer some questions, well, they may or may not do them. Thirdly, you know that when they attempt the questions, they're highly motivated to try and get the right answer in their final exam. So it's a really great place to put some questions. And so they were tracing questions mostly, like the questions from the original 2004 study. And on the basis of those, we divide the students into quartiles. You know, students who did very well, students who did not so well, students who did poor, and students who did terribly. We divide them into those four categories, like we saw before. And by the way, what we're talking about here is comprehension level problems in Bloom. So tracing, certainly, yeah, a comprehension level problem. And then we gave them that explain the plain English question that we just went through. And we classified the answers that the students gave. We were especially interested in giving a correct relational. I've written there, we're especially interested in relational answers. I suppose what I should have had is one more word. You could give a relational answer, but you could give the wrong one. We're only interested in the students who gave correct relational answers. It checks to see if the array is sorted or something like that. And that's an analysis level, as I said earlier. And then our prediction before we analyze the data, students who struggle with the first set of tasks, like the ones out of 2004, will be less likely to provide a correct solo relational answer to the explain in plain English question task 2. So what did we find? Right, so let me remind you, we gave the students some multiple choice questions like the ones that we studied from the 2004 study. And we used those to place the students into a series of quartiles. You know, these students did the multiple choice questions very well, down to these students did terribly. And then on the vertical axis, what we've got is the students' performance on the explaining plain English questions. So what I'm telling you here is, of the students who are in the top quartile on the multiple choice questions, like from 2004, 50% of them gave a correct response, like it checks to see if the array is sorted. Let me. Yeah. Right. 50% of the students in the top quartile told us that, oh, it checks to see if the array is sorted or something like that. Basically, the same percentage told us that in the second quartile as well. And then you start to see the drop off. Very few students in the third quartile could tell us what that code did. And none at all in the fourth quartile could tell us what the code did, could give us a correct relational response. It checks to see if the array is sorted. Now, I will introduce now the other categories, in particular the multi-structural category. Remember, I know I said you don't have to do this in details, and if that was too much information, don't worry too much, but just the multi-structural ones is where students can tell you what the lines do, but they don't tell you what the whole thing does. So what you found was that amongst students in the top quartile, they either told you, oh, it checks to see if the array is sorted, a correct relational response, or they gave you a multi-structural response. And that was a little surprising. I expected the top quartile students to do better than that, but you know, that was interesting to find out. It's pretty similar in the second quartile. Most of the students who couldn't tell you what the relational thing told you what every other line did, or most lines did. Then it starts getting quite interesting as we drop down into third quartile. Some of them, about 20%, could tell us that it was checking to see if the array is sorted. But actually about 2 out of 3 of those students, 2/3 of them, could give us a completely, could tell us all, most, if not all, the lines of code what they did, but they couldn't go that one step further and tell us the overall purpose of the code. And by this stage in the third quartile, we're starting to see some students who can tell us what parts of it do, but but not a lot of it. And finally, in the bottom quartile, none of them could give us a correct relational response. Surprisingly, over 50% of them could tell us what every single line did. I was surprised by that. That at least, so these students have learned something, but they just haven't learnt to abstract from the lines of code to telling us the purpose of the code. A lot of them also couldn't tell us, 40% of them couldn't tell us about what a lot of the code did, and some of them couldn't tell us really anything. But this was a kind of, in a way, a pleasant surprise. Although they couldn't tell us what the code did, they did demonstrate an understanding of what each line did. So some of you might have objections to the experimental method here, and so the students might not have understood the instruction to them and so on. Let me tell you that, after we did our first iteration of this, we did 2 or 3 more, and we refined the experimental method to make sure that the students understood what was required of them. And at the end of it, what we felt we'd established was that there was another stage in this hierarchy where, students could successfully trace the code, but there were students who, despite the fact that they could trace code, they could not see the overall intent of the code. They couldn't see the forest for the trees. Now, we argued in our papers at that time that if students can't see the forest for the trees, then they can't write code. Their problem is not the problem-solving problem. The problem is not they can't write their own code. They just don't have the mental skill to get to that level of problem. We said that we expected that the students who could do this could possibly write code, but students who couldn't do this could not write code. But actually, if you think about it, our experiment asked students to trace code, asked students to explain code, but there's nothing in here about writing. So really, that was us speculating that was a problem. So that was our second trip around the cycle. I'm waiting for something to appear. Is there something else that's going to appear? Maybe I have to hit the space button. Oh, there you go. Yeah, there was something of an empirical method of starting to appear in our work. We invented the explain in plain English question. Invent is a very pretentious word, but okay, we used the explain in plain English question. Was there any theory? Well, you could argue that Solo was theory. I think that's a bit grand. Solo is not so much a theory. It was just a handy way of classifying data, but it led to theory. Let me tell you that. We probably won't get that until tomorrow night, but there's a little bit of theory creeping in maybe. And then finally, of course, we published a bunch of papers between 2006 and 2008 describing this sort of work. So we're now making progress. We've now reached a point where, through a couple of iterations around the research cycle, and only by sticking questions into final exams, we're starting to develop a picture of what the problems are that students have. McCracken said this was the problem and the only problem. What we've established now through 2 research cycles is, in fact, there's a couple of other problems going on with students. That was our second trip. Yeah, okay. So perhaps it would be merciful at this point. How long have we been going? Bert, anybody else? Would you like to make a call as the organizer? Should we break now, or should we just... Let me show you firstly how far we are into the talk. Here we're at 45. View slide sorter. Slide 45 is, so we are here. And you'll see I've got something down here at slide 59 labeled end of talk 2. So, we've got a few slides to go, but I don't know. Do you want to make a call about a break now, or should we?
I think we can really take a 10-minute body break that you can drink a sip of water, because it's already more than an hour that you're talking all the time, hour and a half. So I think you can really have a break now and get maybe a cup of tea or something. And then the other people can also get them some tea. Then we will start again at in 10 minutes from now.
Yeah.
Will
okay,
that be enough time for you? Yes, 10 minutes.
Okay, 10 minutes. See you in 10 minutes time.
Yes, and I've received some questions anonymously already. We will, after Prof. Lister has presented it, we will tackle the questions that has been posed. So if you want to send in an anonymous question that you don't want to put your name through, I know there's lots of, I understand why some people would like to pose an anonymous question. You are more than welcome. We treat it completely confidential, and we will post it on an academic way. So then maybe you're more than welcome to email me. I am here. So thanks. And you can, if you require my email address, it's in the chat. For those people that joined late, just watch the chat. So thank you. We'll see one another at 10:15.
Prof, can you take a question quick?
Sure, I'll be happy to.
I was just wondering, how do you feel about high schools where we don't have an N of 30 for such research?
Where you don't have a what, sorry?
N of 30, and in other words, more than 30 students, or at least a decent sample size.
Oh, I see.
We have classes of less than 30 usually. Yeah.
Okay. Well, the next major research result I'll present will be with a sample size of around 30 something, I think, from memory. So there's an encouraging sign. You certainly don't need to have samples of hundreds of students to do good work, as long as you can do a statistical test to establish significance. It doesn't really matter what your sample size is, as long as it passes a significance test. The other thing I'd say is, of course, I'd encourage you to combine your if you can find some other people some other teachers who agree with you about, something's interesting, and you all agree to run a test, a question or something for all your students, then you can combine data to get a bigger sample.
Thanks, Prof.
So does that answer the question?
Yeah, thanks.
Good. Yeah, maybe I overstated. I mean, it looks good. It intimidates people to say 500 students, but it's not necessary to have that many.
And more qualitative methods?
Oh, qualitative. Well, stay tuned for tomorrow night.
Okay, cool. Okay, great. Thanks.
Yeah, definitely. I love qualitative work. Really, I think we should be doing both, because in a sense, statistical results don't actually tell you something until you can relate it to students, and you relate statistical results by qualitative research.
Great. Thanks, Prof. I'll wait.
You're welcome. So we're at 17 past. Bertie, Yossi, whoever is, should we start up again?
Yes, I think we can start again. Okay. And then we will start with the questions after you finish this end of talk 2.
Okay. Right. Am I still sharing the screen? You see
yes, we see everything.
A hierarchy of student difficulties. I just backed up a couple of slides because I just want to remind you where we were. So after this second trip around, we felt that we'd added another element to the hierarchy. And, so the point I'd like to, there's a couple of, in many ways, the key point to make out of this whole talk is not so much the results, but our method. And that is a bunch of people getting together, of like-minded teachers, discussing what they're seeing, theorizing, speculating, if you like, about what their students can do. And then, and here's a crucial step, we then say, well, what sort of exam questions could we ask in order to prove or disapprove our particular intuitions? And doing that, we had added, to Mike's stuff, we'd added a couple of levels in this sort of taxonomy of difficulty, if you like. All through a bunch of like-minded teachers getting together and talking and then running an experiment. And for that matter, following on from the question I just answered, doesn't have to be a bunch. You could have an idea of your own and run it with your own class and publish that as well. So that's really the big take-home message. But as I was saying earlier, the trouble with by the end of the second pass through was, I better back up for that. We had established that connection quite firmly, I think, in the second time through. There was a relationship people could trace, but they couldn't necessarily tell you what the code did. But it was speculative to say that there was a connection from that to being able to write. So that's what we started to worry about coming into our third iteration. And here we go. So in our third trip around, well, of course, the papers that we'd published in the first bracelet years, 2006, 2008, became the input, if you like, to our next trip around the cycle. Whoops, something was about to appear, was it? Oh, yes, and of course, our output was the papers we published between 2008, 2009, 2010. Now, what was our method this time? Well, no big surprises. We effectively added to the existing experiment. Again, we gave students some tracing tasks to do, and while we're at it, that's comprehension level, Bloom. And we asked one or more explaining plain English tasks, and I've asserted that they were analysis level of Bloom. And all we did was add to that, well, if you want to see a connection between explaining and writing, well, add a writing problem. We asked the students to, solve one or more writing tasks. which is kind of at the application level. And by the way, if anyone's, I know I'm using the old words, analyze and apply would be, I think, what the revised taxonomy uses. Some of you might be a little bit worried that I'm essentially seeing if there's a relationship going up from analysis to application. Not really. As I said yesterday, the Bloom levels fall pairs, and Bloom was never too worried about, you know, which came first, application or analysis or synthesis and evaluation. Though their ordering was interchangeable as far as he was concerned. So there's no real dilemma in saying, you know, is there a relationship from analysis up to an application, problem like that. Anyway, so we've got the 3 tasks. Give the students that. Now, in a final exam, once again, we're just using our final exam. And our prediction was that there would be some sort of relationship between tracing and explaining, the ability to do those skills and the ability to write. Now, I don't literally mean a plus sign like in addition. We're just saying tracing and explaining. Maybe an and sign would have been better there. Okay, so let's see what happened. Now, due credit, I have to give, being a researcher, I have to give due credit. The first paper, I was one of the several co-authors, but the first paper was first authored by Mike Lopez, who did the statistical analysis in 2008, but I'm not going to present you with that one because that one's harder to understand than another paper. So I'm going to go with the second paper. And that was a paper I did in conjunction with Anne Venables and Grace Tan. I didn't have time to write a slide for it, so that's why it says, it's instruction to me, tell the story about Anne and Grace. Effectively, Anne and Grace were 2 very dedicated teachers teaching at another Australian university, and they came to me and said, hey, I've seen the work you've been doing with the bracelet people on that sort of stuff. We'd like to do something like that too if we could. And so we effectively did this experiment where we gave, in the final exam at Anne and Grace's institution, we gave the students 3 tasks. Anne and Grace, by the way, designed the 3 tasks, all the tasks in their own exam. They wrote their own exam, but we just chatted about, you know, the design in general terms. And then we got the results. And that's, by the way, I'm just repeating what I said to the gentleman who talked earlier. How many data points did Anne and Grace have? So this is data from one institution. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28. There you go. So roughly 30. I might have miscounted.
Thank you, Prof.
Yeah. Now, so what did we do? It was very simple. It was just a linear regression. We said, what did the students score on tracing questions and what did they score on the explained questions? There were several tracing questions and at least 2 explained questions, but that's the detail that I don't think is important right now. Don't worry about these coefficients. They're just an artifact of the whole multiple regression process. Just think of it as score on tracing and score on explaining questions combined. And you can see it runs from up to, I guess because it says 30, the students could, no, I don't think so. I think these students were scoring the maximum possible mark. So 20 something on the tracing explaining questions. And on the left-hand axis, what we're plotting is the performance of the students on more than one writing task. I can't specifically remember how many there were or what they were. Okay, and then we just put a line through it, linear regression. We'll debate this now, I suppose, but some of you might think that's a bad fit to the data, that line, or some might think it's a good fit. Let's start with the raw statistical consideration. Firstly, it is a statistically significant at the 0.05 level result. That writing was predicted. I'll put predicted in inverted commas because strictly speaking, you could argue that writing was predicting this the other way around. It's a correlation, but I'll talk in terms of prediction if you don't mind. So it's statistically significant. Now, if you're not familiar with this in stats, R squared is a measure of how well your points fit the line. And an R squared value of 0.66. Well, if you were doing a physics experiment, you know, from physics experiments at high school, I remember rolling ball bearings down an inclined plane and measuring something. I can't remember what that was, but whatever it was, you might expect a tighter fit to the line because physics is like that, or certainly Newtonian physics is like that. But people are messy. People are very, very messy. You never get, well, I can tell you that psychologists start getting excited when they do experiments with people if they get an R squared of 0.4. That they regard that as a great fit. So an R squared of 0.66 on this experiment using messy people is by statistical standards, by psychological standards, is a great fit. And if you still don't believe me, and that's fair enough, let me put it to you this way, qualitatively. I've drawn a big circle there because what I'm trying to point out is that nobody who did poorly on the combined tracing explaining course, nobody who did poorly in that did well on writing. Just nobody. And equally, nobody who did well on tracing and explaining here did poorly on writing. And we can debate whether this is a good result or not. I have been claiming it is for some years, so I think I'll leave it at that for the moment, unless some people want to later debate it with me. It's a great result. As far as I was concerned, we demonstrated the relationship to writing. And remember, before I get to anything else, these are just questions in an end of semester exam. You can do something like this yourself. All we're trying to do is move our understanding of our students along by using our exam not just as a way of assigning a grade to a student, a point score to a student. We're also using it as a diagnostic tool to try and figure out what's going on with our students and why they're having problems learning. And all we're doing is putting questions in an exam that we have to write anyway. I just want to repeat my slogan from earlier. A good exam should teach you something new about your students. It's not just a way of assigning a point score to students. It should teach you something about how your students are learning. And usually, to back up just for a second, most of our analysis boils down to giving different types of tasks to students and then analysing, well, they can do well on this, but they can't do well on that. It's comparing their performance on one task with another. Okay, so by this stage, by our third trip through the cycle, we felt that we'd established this, that there was at the bottom there were students, well, not necessarily at the bottom, but low on the taxonomy, students aren't able to trace code. Then further up, we think that although some students can show they understand what the blinds of a piece of code do, they can't see what the overall algorithm is that emerges from that code. And we think that's a prerequisite. Well, we think that graph that I just showed you, that one there, was a pretty solid indication that you need these sort of skills, both of these skills, to be able to write code. Oh, okay. Actually, it's not a linear hierarchy like I've drawn there. That was a little bit of surprise. That was what we hypothesized. It would be a linear hierarchy. Turned out it was actually a little bit more complicated than that, and it won't take long to explain that. If you look at a student's score on tracing questions and look at their score on writing, so tracing and writing, there's actually quite a weak correlation. And equally, if you look at just the score on explaining questions and writing questions, it's a weak correlation. It's the combination of the two that turned out to be the really strong indication of performance in writing. You need both skills. You need tracing and explaining to do the writing. Oh, and furthermore, I think that arrow is supposed to grow by itself. Let me see if I got my... There we go. Yes, look at that. Or look upon my PowerPoint and despair. What we found was that, initially students, students reach a point where they can trace, or I guess I'm asserting this more than saying what we found. Students, and then on the basis of tracing, they slowly develop the skill of reading code, sometimes often by tracing lots of code. They slowly begin to understand, code in a more abstract way by being able to explain what it does. And then finally, after they got pretty good at both of those skills, then the code writing skill begins to emerge. Well, because Microsoft Teams, I don't expect to. The first take-home message many slides ago was explicitly teach and test tracing. It's a foundation skill. But make it fun. Try to make it fun. The second take-home message. Well, yes, tracing skill alone is not enough for code writing skill. Tracing skills helps develop explaining skill and understanding of code. And I'll assert that last point here, not quickly, be patient. I think we overestimate at tracing and a lot of practice then at explaining before they develop. It's quite a good skill. And only after, and that's really what I'll talk about a bit about tomorrow. And then only after they've got both skills do you start to see a ability to write code. Now, look, if enough monkeys type long enough, eventually they'll type Hamlet, right? Is the old expression. If you sit a student down in front of a computer and tell them that their exam, their passing, failing will depend upon them writing a piece of code. Of course, they'll try to write a piece of code. But what will they do if they can't trace and or explain? They'll try their hardest as best they can, and they'll probably hand in a pretty incoherent program after a very incoherent approach to writing. What we're really saying here is that only a coherent, methodical approach to writing, that will only appear after students have got these two skills. All those students that you've seen hammering away and randomly changing their code, and you exhort them to be more methodical. Well, you've got to do, I think, more than exhort them to be more methodical. You've got to teach them the underlying skills that will make them more methodical. If you can't trace, let's forget to explain it. If you can't trace, how can you debug your own code? I think that's an obvious question, and it's worth repeating. If a student can't even trace their own code, how are they ever going to debug it, other than by random permutation? Okay, so tomorrow we'll take the fourth trip. Do I have a little preview? Oh, no, I'm just going straight to my conclusions. A good exam should teach you something new about your students. If you've forgotten everything else about this talk tonight, I think that's the lesson you should learn. Look to your exam to teach you something. Design your exam. Write questions so that next semester you'll know a little bit more about how your students are thinking. And that's the end.
Thank you very much. That sounds very, very, very good. Bertie, I think you can start with some of your questions that you got.
All right, thanks. Some of them I think I've actually received 3 questions where documents was attached, so I tried to anonymize it to the best of my ability. But while we are here, while I'm just getting it ready, one was sent in for Prof, and Prof listed the question read as follows, while I get myself up. Oh my goodness, now I've lost it. Just 1 second. 1 second. Oh, it's the question read as follows. Considering that in the first semester at university often covers a lot of the work that we do in our 3 years at school programming, grade 10 to 12, can we or could we consider our learners as that is in school and regard them as novices? Professor, what's your take on that? True or false was the question?
Good question. Could we regard them as novices? I mean, I did show a slide quickly yesterday. And let me see. If I can share, Bertie, I think I'll share again. I think that's the right. Are you seeing a picture of a rocket right now?
Yes.
Yes, you are. Good. Now, let me see. This will be quick, I promise. I don't want to take two. This is talk 2. Tomorrow's talk 3. 26th. That's the one, is it? Yeah, this looks like it. View slide sorter. Now, this is a question that I was involved in writing this exam for our high school students in 2013. So this is their end of high school. They've done 2 years of software design and development, a subject called software design and development, when they sit this exam paper. And this is a multiple choice question that we gave them in the exam. Length is set to 0, breadth is set to 0, area is length times breadth, and then we initialize length and breadth to something non-zero. And the correct answer then is, well, when this code is, what the values in length, breadth, and area after this code is finished, well, length and breadth will have 5 and 4, but area will be set to 0 because we did the calculation, didn't we, before we did that initialization to 5 and 4. But in fact, 30%, almost a third of the students who'd studied this high school subject for 2 years chose option D. So my first point is, rather than accepting that students coming into the university are not novices, I would test them. I would give your incoming students a test. And so rather than whether they've done obviously it'd be voluntary because the people who haven't done any programming at all, there's no point in them doing the test, but the rest should do this test. And then you should make a decision on the basis of a test, whether they are novices or not. As a policy decision at UTS, we largely threw into the one classroom students who had done high school programming and students who had not. And I used to begin, part of my first lecture was to simply apologise to the students who had done some programming that they were going to be rather bored for the first few weeks while I covered what they already knew, but there wasn't anything else I could do. At the policy level, the university decided to run one course. And I was not going to leave behind in lecture one all the people who, we advertised the subject as an introduction to programming with no prior experience in programming, and therefore that's how I taught it. Unsatisfactory arrangement. I guess you've got to look at the paperwork. If your subject at your university is listed as being an introduction to programming with no prior experience required, then that's what you should teach, in my view, because the people are buying your course on the basis of the promotional material. Is that ideal? Probably not. So then talk to your management about having more than one class. I'll tell you one thing what we did do was that we were able to establish, or a colleague of mine was able to establish, who in my class were not just students who'd done some programming, but who actually were quite good at it. And she used to run a project off to the side where these students worked on actually they worked with industry clients, those students. So we moved them off into a side project and gave them a productive learning experience that way. That's a bit extreme. You may not want to do that sort of thing. It might be too hard for your institution, but you could always move those people over into some sort of a side project and try to keep them entertained that way. Does that answer the question?
Yes, I think you've answered quite a lot of it. I think the question was a lot around the emphasis that maybe we tend to expect too much of high school learners and maybe have concepts in a high school setting that is maybe, too advanced or something like that, to like you stated, maybe many of them will then find the first semester not such as a challenge, but we need to consider everybody that comes in to do a course. And at our university, that's a typical reality, where we even have some foundational bridging courses to assist the students even more. There was another question, Prof. Raymond, based on your university. Could you just give us a 2-sentence overview in the department that you was, up until which level did the students go with programming? Yesterday you showed us some examples of apps that students developed, but can you just give us a 2-minute background or a minute background in a few sentences about what did you do in your university? Because some of the colleagues, and that was a question from one of my colleagues, asked, where did you go up to? Because I think in their mind they want to do relate your university to what we're doing and just seeing how it compares.
Okay, so you mean the whole of degree? How do they progress?
Yeah, just a snapshot overview of the type of programming, that they only have one subject programming, or that there are 2 or 3 different, that type of.
Okay, so the students do a degree in information technology, which can split, they do effectively a common first year, and in that first year there will be 2 programming subjects, one in first semester, and most of my experience was in that first semester, and then there's one in the second semester. At the end of that first year, students start to decide what major they will do as part of their degree. And effectively that boils down to, well, 3, I think, which is software engineering, on actually 4 these days, software engineering, systems programming, if you like, and as a second one. Third one is kind of information systems, and then the 4th, which is relatively new, is data science. I can't say much about the data science one because that was quite new and I didn't have much connection with what programming they did in that. Information systems people tended to not do any more programming after the first year. The computer systems people and the software engineering people went on to do quite a lot more programming. The very first thing they do in the 3rd semester would be a fairly orthodox data structures course. And like many data structures course, they also introduced the second language to the students. So they did Java, and when I was teaching, they did Java in second semester. Then when they did data structures, I think they did it in C++. Then after those, that was like the first 3 subjects that introduced them in a very rigorous way to programming. There are a plethora of other subjects that teach them things like, you know, how to write programs that will run across the internet and so on. And I couldn't enumerate all the sort of subjects that do that sort of thing. All I can say that by the time they reach their 3rd year, we have what we call the Capstone Project. You may have it too, because it's quite a common thing to do in lots of countries. And so they would be given a large project to do over the course of at least 1 semester. I think it was only 1 semester by the time I finished. Sometimes it ran for 2 semesters, the entire 3rd year. They would work in a team. In some cases, they might have a real industry client. In other cases, they were given a pretend client, if you like, which may have been me or another academic. And they effectively simulated a whole software development process of, you know, listening to the client, defining the requirements, you know, then building the software and so on. Does that answer the question?
Yes, Prof. And I think a lot of my colleagues and from the other people here from other universities and universities of technology will completely relate to what you've stated. And it's mostly the same in many of our universities as well. So thank you. It was just one of my colleagues that asked that, and I think you've answered it quite nicely. It's a bit out of the scope of the talks, but I mean, it gives us some time to relate and some time to get into some discussions. I would like to share my screen because for the other questions that I have, people have sent me in documents, so I try to anonymize it to the best of my ability because I don't want to put names, and it's just for the sake of the question. So I'm going to share my screen and have it open, and then we can discuss it through. I really double-checked and triple-checked to see that it's really anonymous, so I'm going to do that. Let me just see which one we can take. So here we are. That's it. Can everybody see my screen? Prof, can you see?
Anonymous question. Yep.
There we go. So the one that was at our university, we have an ordering type question in our learning management system. As seen in the example below, pieces of code segments are given to the students, and it's expected of them to arrange it in the correct order to solve the problem. What levels of blooms would Prof say this question will be associated with? Most students struggle to answer these types of questions correctly, even though all the code is given to them. Is this on a higher level of blooms? I enjoy these types of questions for online assessments, since students are not able to access the computer to write and submit code. So this is just a typical, the user must enter something, and then it's a Java program import, and then they must say, if you want to write a program like that, they will have some paper to conform it. And obviously, that will need to be your first statement. Then they need to select, for example, where's 2 now? This is the next statement, and they need to order it in the correct way. So you give them fragments of code, and they must order it. So how would you see, and how would you potentially classify a type of question like this, where all the code is code is given and it's basically scrambled and the student needs to descramble it.
Okay, but by the way, in the case, at least in Australia and New Zealand, and I think these days in America, these types of questions are known as Parsons problems, because the first time we saw them in Australia and New Zealand, and probably America, they were being promoted by somebody called Dale Parsons from a polytechnic in New Zealand. So, by the way, if the person's asking if you want to know more about what people have found using that sort of a question, you might Google Parsons problems and see what comes up. Now, what category are we going to put it in? Well, I shall make an assumption, which is that the assertion was made that all the necessary information is provided. So on one hand, that would argue for comprehension. On the other hand, it does look quite difficult, doesn't it? Now, difficulty doesn't necessarily relate to Bloom levels. You can have an easy or difficult application question. You have an easy, difficult analysis question, an easy, difficult comprehension question. So I would say this is at least a difficult comprehension question. I'm tempted to say it fits into the application. I suppose, well, there you go. See, I mean, you might argue in a way it's analysis, isn't it? Not that I care too much about whether it's application analysis. The choice between those two categories, because the Bloom levels come in pairs, I'm never too stressed about whether somebody says, well, this is really an application, it's not analysis, because it just doesn't matter that much. So the real thing comes down to, is this comprehension or is this application/analysis?
Thanks.
I think I'll stay with, it's a really difficult comprehension question. I'll stay with that. But if somebody disagrees with me, I probably won't challenge them.
What I would like to just point out, and this you've pointed out very wonderfully, Professor, because in the domain that I'm working with, there's often a misconception regarding the difficulty level of a question and the cognitive level of a question. So while we are on that point, can you maybe, I know it's on the spot, but can you maybe give us a little bit more of your thoughts on that, if possible?
Yeah, I think that's going to be an easy question to answer, Bertie, because I'm not sure I have many thoughts. I suppose one place that you might go to think about it, so is perhaps this is where the revised taxonomy may have an advantage. Now, as you've gathered, I am partly an old-fashioned stick in the mud who learnt the original taxonomy and never felt a great need to modernise himself by having a look at the revised one. The revised one, I regard the revisions to the level naming and the reversal of synthesis and evaluation and it's relatively trivial changes, but the really substantial change that came with the revised taxonomy was a whole second dimension, and I can't, beyond my awareness that there's that second dimension, I can't say much about the revised taxonomy, but that might be a good place to go and think about. It might offer some insight into what's the difference between a difficult and an easy comprehension question, or what's the difference between a difficult comprehension and an easy application question. That's the best I can do.
No, but that's already food for thought. And thanks, Prof. Let's move down to the other one. Anonymous. This one we did do, the true or false one. If Prof has background on SQL, how would one classify different SQL statements? A join, in my opinion, is of a high cognitive demand or higher cognitive demand than a select, for example, with an aggregate function. Any thoughts on this? I add some questions a part of a larger exam that our grade 12 learners write. So these people added a question like here, and then they get, for instance, different types of SQL questions. Now, this is typically from our high school exams, and they just ask that if you, for example, looking at SQL, would Prof think that questions relating to containing joins in tables are of a higher order or of a lower order when you just do a typical select, for example?
Yeah. firstly, do I know anything about SQL? I know a little bit because I had to teach introductory database for a number of years, about 10 years really. And but I also, I'll say this caveat. I mean, I know nothing more about databases than what I taught in my introductory course. So yeah, I do know some simple SQL queries. Now, it depends, I think, on how you phrase the question. When I used to have tests where the students had to write SQL queries, and usually in those I would nominate that by some method what type of query the students had to write. For example, was it a join, or did it involve a group by, or something like that? So in that sense, I was, if you nominate what's required, what sort of a operation, what type of query, then I think you're heading towards comprehension, assuming that in nominating the type of query, you've provided all the necessary information. I used to provide students with an ERD, and I think if it was a join, I would probably nominate all the tables that were required. I think I did. I'm not sure. So you're heading then towards comprehension. If, on the other hand, you don't nominate what's required, if you just phrase it as give me a list of all the different products that we make and tell me how many we've sold of each one, starting to sound like a group buy to me. If you don't mention group buy, if that's what you give them, I think you're heading into application, because now they have to realise that a group buy is required.
Yes.
Does that answer the question?
Yeah, fantastically, Prof. Fantastically. So even then, looking at the group by and looking at, for example, a join, it depends on how the question is phrased. If two tables must be joined with a primary key and foreign key, and it is explicitly stated in the question that type of information is given, then it lowers the level, as if when the student needs to figure it out, for example, on his or herself by inspecting the relational diagram that's given. Because typically, for school kids, the relational diagram will be given. Then we've got another final one. I think this is all right. Dear Prof, what are your thoughts on a question paper that assesses the concept of OOP, but the progression from one question to another are dependent on the success of the learner of the first question? I think this question forms part of a practical exam that counts 120 in total, of which the OOP question count 80 marks. So I had a quick scan when I get it. So what I have is a bigger object-oriented programming scenario. Then it seems they give the scenario with a UML diagram. Then there's a question 2 where they design a new class there. It looks like student with some methods over there, and a toString method and so forth with accessors and mutators. But then the question gradually builds on. Question 3, then create a new class called grade, and it then builds up. It seems that you are going to require the answer of the previous question to kind of be successful and to implement. Yeah, here they talk about create an array to store up to 50 student objects, and then another array to store up to 5 grade objects. So it's kind of, it seems like aggregation and so forth. I didn't look at the question in detail. I was just too scared. I was just anonymizing everything. But what is your take on that?
First, I got a question. Is this a paper-based exam, or is this something they're doing online?
No, this is practical. This is a practical exam.
So it is an online exam.
Yeah.
Okay.
I sit in front of a computer, and I know it's part of a 3-hour exam where this OOP question counts about 80 marks, and there's 40 marks of SQL statements that's in the beginning. So this is a practical, what they call a practical exam. And it's a high school, and I can tell you now it's from our schooling system.
Now, I think I'll avoid saying whether it's good or bad. I'll talk about strengths and weaknesses instead. The strength, I think, is that you really are, in principle at least, in theory, separating the students out into those who can do some of the basics but can't do the more complicated things. And that's good. The
Okay.
weakness, I think, is if you've got a student who basically can do some of the harder things, the higher level things, but for some reason they've just made a dumb mistake in an earlier one, and they can't seem to be able to fix it. And we've all had programming experiences where we've made a mistake, and for some reason, we chastise ourselves later when we eventually find it, or somebody finds it for us because it was a dumb mistake. So I'm a little bit worried about students who are actually capable of doing some of the higher levels, but they are prevented from doing so because of some dumb mistake under exam conditions. So I'm having a bet both ways. In principle, probably my argument would be this may be impractical because it involves so much reading, but I would prefer to ask here's another one. How about this? If the online system was smart enough that the student could attempt something, one of the earlier stuffs, and then they can't do it, and eventually they just say, I can't do it, give me a solution, and you give them that, and then they can go on to demonstrate the high levels. That would be quite reasonable, I think. The hard thing there is that most students are gamblers by mentality, and they will back themselves to find this bug at some point rather than just to concede and give up in order to get a higher level. I think the type of question I'd like is one where you actually, in one question, you get them to do something at a low level, and then in the next question, which is a different scenario to the first question, you provide them with, you then ask them a higher level question from that something that's higher level than what you asked them in the first one. The problem with that sort of style, of course, is that it just leads to a lot of reading, and they have to assimilate a lot of material in order to answer the questions. And I don't know how long you said the practical was, but that could be difficult. They may not have enough time to do all that reading. So is that an answer, or should I
Yes,
can I elaborate
Prof,
on that in some way?
No, that
Sorry, Prof. Lister.
Yep.
If I could just interrupt and give a bit more context.
Yes, please
Hello?
go ahead. Yep.
Go
ahead.
Yeah, it's a 3-hour exam, but it's not marked as doesn't compile. You don't get any marks, or doesn't run. The code is actually marked piecemeal, so individual methods and things like that. So the ability to score marks throughout is there if they just keep coding and write some code.
Oh, okay. So just let me clarify. When you say it's marked, it's like a manual inspection. You actually look at the code.
Yeah.
Yep. In that case, I think that's a good way of testing. Yeah.
Yeah, it seems to work well, and I think if you look at some of the graphs of our distribution, that's why I think we're getting a lot more in the middle. Yeah. Because we do give them part marks. Even for an SQL query that's a complete join, like even if you just select the right fields, you'll get 1 out of the 6 marks or whatever. Yeah. So it's all manually inspected by markers.
Yeah. Oh, good. Okay. So I guess, yeah. So just for the benefit of other people, if you had an automatic system which wouldn't allow the student to move on to the next part of the question until they actually got the first part right, I'd worry then about those students in that automatic approach. But given that you're marking manually and exercising some judgment, I think that sounds like a really good way to test students.
Yeah, and as for the reading, I know they do get 10 minutes reading time prior to the exam, so they can read before they start. But your reading length is always a problem. I think, there's some of our exams which span kind of 15, 20 pages. But the language is checked quite carefully there as well for readability and things like that on a national level. So, yeah.
I have been known to sit in meetings, and because you said this practical is 3 hours long, is that right?
Yeah, 3 hours long.
Yeah, okay. I sometimes query whether what we're really testing is the bladder capacity of our students in a 3-hour exam, but
I think a lot of our school leaving exams are 3 hours.
Okay. Well, as long as that's the environment they're accustomed to, that's fine.
Yeah,
I'm sorry.
They are accustomed to it.
By the way, in Finland, they sometimes have exams that run practically the whole day. They even bring food into the exam room. Yeah, they bring food into the exam room in Sweden. They cater their exams.
Prof, yes, there was another question here in the chat room. And do you track the performance of your students at the end of their qualification? For example, if you look at the finger painters, how did they perform towards the end of the qualification?
Okay, I can't. No, as far the furthest I went was the third subject. I had a slide yesterday, I think, where we showed that some of the students, the finger painters, so they got the lowest passing grade in my subject, but they did quite well in the third semester. I could find that slide and show it again, but I think I'll just leave it since it's in the first talk. I'll just say qualitatively, a lot of them, of course, got another bare pass, but you'd expect that, irrespective of how you teach your students and how you assess them. The students who get a bare pass in the first subject, if they pass in later subjects, you'd expect a lot of them will get another bare pass again. But some of them did better than that, and some of them, in fact, went on to get the highest grade. And we have 4 passing grades, so some students with a bare pass in the first semester went on to get the highest grade in the third semester. So they're not streamed, if that's kind of what the question's getting at. I can't go beyond the third semester. I have no data about how they go from then. The only thing I can relate is one interesting anecdote. We had a student who volunteered for, I'll talk a little bit about Donald tomorrow. He volunteered for a study that we did where we focused very much on individual students. And Donald was a fantastic student to study because when he came to us, he was terrible. His programming skill was just almost non-existent. But Donald had this wonderful attitude about learning. He was very dogged and determined. And he went on to do quite well in programming in his degree, and in fact, then went on to work as a programmer. So I will maintain that anecdotal story is an indication that if you're patient and teach the basics well, students will teach a lot of the rest of the stuff to themselves. I think where we fail a lot of the time is we rush to get them to writing large quantities of code, and they don't have the basic skills. I'll go back to what I repeated earlier, which was asked earlier, which is if a student can't trace their own code, how are they going to debug it in the early years? So I think we've got to make sure the foundational skills are in place, and then they'll teach themselves a lot of the rest.
Thanks, Professor.
Is that an answer to the question?
We've got another question. Yes, it does, for sure. What did the lady posted? Any thoughts on the length of reading a question? What is your opinion, or do you have any ideas on best practices with that regard? So how long, the length of the reading? You did allude to that, but any ideas or any further thoughts?
Sadly, this is could be the same in South Africa, but sadly in Australia, IT degrees, a lot of high school teachers who advise students, and a lot of parents who have kids who are fairly technically strong but weak in areas like English and so on, advise them to go into IT because, well, there won't be much reading in IT. And in fact, we know there's a lot of reading in IT. It's poor advice, but that means we do get a lot of students whose reading skills are weak. And I don't think I've ever sat down and done a quantitative study of this and written it up. I'm sure I haven't written it up, but certainly we've noticed, and this is across institutions, and we did this as part of Bracelet, we noticed that the more reading we had in a question, the less likely students were to get it right. And it would seem a lot of students would give up at the reading stage if it seemed too difficult to read. So the less reading, the better. My approach to reducing the amount of reading is as follows. I mean, if I need a scenario in an exam, I give the scenario to the students before the exam. So I try to give the students as much information as I possibly can that's background to any of the questions without giving them the actual question itself. And that's proven to be pretty useful. That's worked pretty well. So the less, I don't know about how long the reading should be, but the less reading, the better. And the way that I have routinely reduced the amount of reading a student does while in the exam is to give them as much of the stimulus material as I can before the exam.
Thanks, Professor. That is a that is a good answer. And I just, in relation, when you talked about the Finnish system where they get the whole day, I know Prof. Van Vieren is still here and some of my colleagues. At our university many moons ago, we used to have a 6-hour practical exam, and the students could bring in anything. They could bring in their snacks, their tea, their whatever. And some of them really made a party of it, and that was always something quite fun and informative, and just to see them completing it. Because for me, it wasn't about the time. I always had the idea in my mind to say that students must be given time without working in a very big, stressful environment to solve some problems. Because when they go out one day, and we being University of Technology, with a little bit more focus on the vocational side, they won't be in a 3-hour situation where they will necessarily need to be or do such a big piece of code. So we normally used to have a 100-mark exam with not so many types of coding or coding required, and have them do it over 6 hours in their own time. And the good ones normally completed it in less than 2 hours, but the other ones had some time to complete it. There's another question on our chat group which asks, dear Prof, what is your take on teaching block-based languages at school level for teaching the basic programming concepts and principles rather than just focusing on industry-type programming languages? That was the one question. There is another question that's a follow-up on this, but let me just put this one as first.
Okay. The younger the student, the greater the more emphatically I agree that they should be using a block-based language. The way it currently works in Australia is that at the primary school level, the national syllabus, this is a bit complicated. Australia has a national syllabus, but then it's often honoured more in the breach than being faithfully implemented by the various states. But let's just stick with the national curriculum. The national curriculum says that at the primary school level, the students will use a block-based language, and then in junior high school, they will, in their first years at high school, they will transition to a text-based language like Python or whatever. I'm not going to buy into exactly what age is best. I mean, I think there could be a high school teacher listening right now who, on the basis of their own direct experience with students, would tell me that students should continue using block-based in early high school. I don't know. I won't buy into that, but I will buy into that the earlier the younger the student, the better they use a block-based. But I will say this, block-based are not a panacea. Students can get themselves into as much trouble with the block-based language as they can with text ones they can. So it's not a panacea. But at least they're not trying to figure out where the semicolon needs to go.
Yes, thanks. All right, then follow up to that is another type of question. In really considering the concept of object-oriented programming, what role does the bigger picture, that means, and then they wrote in brackets, understanding the relationships, part of the whole, the flow, and the integration play in the cognitive demand of the question? Does that raise the cognitive demand? So in understanding OOP in itself, by knowing concepts like instantiation and so forth, does it raise the cognitive demand? Because you need to implement it as part of a bigger picture.
I think the short answer would be yes. But let me then walk slowly backwards from that, mostly through ignorance. As you might have inferred from my PowerPoint slides, my teaching still tends to be, although we did it in Java, we still emphasized procedural type concepts a lot. So I don't, and I have never taught a user interface library like Swing, whatever. So I'm relatively ignorant about this. It seems plausible to me that what you're saying is true, that if they need to understand how the things relate and so on, it's going to move up higher in the taxonomy, but I don't feel qualified to really be more specific than that.
Thanks, Prof. That is a very good answer. And in my own personal capacity, I agree to say that I think students, depending on their age, a third year or second year student that has had some exposure will think about it differently than, for example, a 17-year-old that is exposed to it for the first time, that is still in high school. That was all the anonymous questions that was sent to me. I do not know if there's anybody that still has another question maybe to ask or some comment that they would like to make. Anybody? Yes, I see Mr. Greuters has his hand up.
Sorry, Prof. Perhaps a bit of a controversial question, and you're welcome to not answer it. You started off yesterday speaking about, obviously, the explanation being, well, Prof. List is a terrible teacher. Do you have any advice for, I mean, it's wonderful to say kind of that we want to look at students and user assessments and everything. Is there any way to diagnose like poor teaching and then to kind of rectify that? I think some of us are kind of in charge of other teachers or train other teachers or whatever the case may be. But yeah, I don't know if you have any experience or just an opinion on that.
Okay, there's certainly no shortage of poor teachers. See, I've worked in all my entire career was in universities that aspired to be greater heights in research, and so the management was always harassing people to do more research and to not spend so much time on teaching. I was a pretty awkward customer in some ways for the university because they couldn't quite categorize me since I kept maintaining that I did research. I researched in education, and I saw a lot of people who were at least poor teachers because they were preoccupied with their research and they shortchanged their teaching. I certainly saw quite a few people who, shall we say, had a talent for teaching poorly. They just were not very good at it. How to solve the problem? Hard. I didn't like the way that UTS went about it. UTS effectively tried to improve the standard of teaching and would have rules about what constituted good teaching, and then would coach people on what those rules were and insist that they do them that way. And I guess I was cursed in a way because I was doing research in education. So I said, well, look, I understand where you get coming from with these rules, but they don't apply in certain situations because of. And then you're in a very awkward situation of you seem to be disobeying the management when you're not disobeying them. You're saying, as a researcher, I have a problem. Can we discuss it? I don't know how to solve the problem. There's a lot to be said for trying to force people to teach better, but it doesn't seem to work well. A lot of people who don't want to teach well end up then playing the game of going through the motions of making their teaching look like it's good. And yet, if you're intimately involved with them or their students, they're not teaching well. So I guess I don't know. I wish I did, but I don't.
Thanks, Prof. Lester. That is insightful. I think we've reached, according to our schedule and program, the first part, the end of our first part of the presentation, and we're going to move over now to our next presentation.
Betty, can we first just give a 10-minute break?
Yes, and then Mr. Amabu can come. Joey, would you just like to close this session for us?
Yes, I will close the session. That's why I said I just want to do a break in between that. We just have that people can have a break. But thank you very much, Prof. Lester. I think, Patty, what I also want to suggest that if people has got exam questions, papers, etc., that they want Prof. Lester to give specifically comments on, that we send it to Prof. Lester. that he can just prepare and give us some comments on that from the Bloom's taxonomy. So please, if people can in advance send those things to Prof. Lister that he
I
can
think they can
evaluate
send it to me. Let me be the coordinator, and I will forward it and collate it quite nicely, and then I'll provide feedback. Let's not inundate Prof. Lister. I will collate and then forward it on. I will do that.
Okay.
That's fine.
Can I just interrupt just very briefly? In a sense, I owe Bertie and Joey an apology in a sense, because our original plan was that I should talk less than I did, and then we were going to spend some time looking at questions and me classifying them, and we've run out of time to do that. So perhaps offline, perhaps by email, we'll discuss maybe we should reorganize tomorrow in some way to guarantee that I do things the way that you'd like them. One simple way might be to reverse the ordering, so that we start with me looking at questions tomorrow, and then I give a presentation after we've done that for a while. But that's just a suggestion. Perhaps we'll take that offline by email.
Yes, that's fine.
That's a good idea. That we can. We've got some time now, a little 20 minutes, but I don't think it is worthwhile to start with things now. So I think we will rather a break now and then start a little bit earlier with other talk as well. But I think it is very important that what we learn all the time, we learn so much from you every time and all the questions. Thank you so much for your time and the time, preparation time, etc. We really, really appreciate it. So thank you, Prof. For today, and then we'll see you again tomorrow, and please feel free to attend the next session, as I think it will also be nice for you to see the work that these people has done, the person has done at UNISA also as part of his research. So I think we will start, we will have a 15-minute break now, and then we can start, or a little bit more than 15 minutes, then we can start at 11:45. Will that be fine for everybody? I just want, before we stop, I see there's another thing that a person asked. Prof. Lister, do you have a podcast or a blog, etc., that people can communicate with you?
I don't have a blog. I can give an email address, I suppose. Just bear in mind that I can be pretty slow with getting back to people by email. But if anybody who's interested enough to have put up with me through these first two talks, I'd be quite happy to take an email from them. So I'll give you my address, which is raymond.lister@gmail.com. You can email me there. I just warn you that there's quite a few names I see listed. I can't promise to be prompt in getting back to you.
But thank you very much, Prof. But we will see you tomorrow when we start again tomorrow morning with your presentations at 9 o'clock. But please feel free to attend the next session.
Oh, I certainly will be listening, lurking. I enjoyed yesterday's tremendously. It was very inspiring, and I'm hoping that today will be the same. So talk to you later.
Thank you very much, Prof. Then, yes, Bertie?
So just a quick, we will have Mr. Amabu presenting at 11:45 for half an hour, and then Dr. Roxanne Bailey thereafter.
That's correct. Okay. Did I go on to, is it too late? What is the program said? Sorry, Bertie, I'm a little bit confused. What time was the program?
Our program has Dr. Bailey presenting at 11:15, and Mr. Amabu was actually scheduled for 11. But I think if we have a small body break now for 15 minutes, then if we start at 25:02, then it will be possible for us to put in Mr. Amabu and still be in time with our normal schedule.
We'll do that. Then we will start with Mr. Amabu. I will start just reading his things at 11:30. Okay.
Thank you. See each other.
Thank you very much. See you at 11:30. Thanks. Bye.
Bye.
Hello? Yeah. That's finished?
Karina, jy's unmuted. Good afternoon, everybody. We're so glad you're back here. And it's good evening in Australia, but it's good afternoon here. Maybe just a little bit not good afternoon, as it's still 11:50 and not 12 yet. Thank you very much for everybody that's already back here again for our second session for today. Our second session is going to be done by Mr. James Ramabu. Mr. James Ramabu completed his diploma in software development in 2008, his degree in 2011, and his master's degree in 2016 at UT. He's currently busy with his PhD at UNISA, and his topic is an animation-based pedagogical framework for struggling introductory programming students. He has been a lecturer in the field of computer science since 2010, teaching programming subjects and database modules. Most of his publications are all around computer science programming education. Welcome, Mr. Ramabu. We're very glad that you can also present your research that you've done. It looks very exciting. Thank you very much. You can upload your slides if you want to.
Hello, James, are you there?
I see he is here, but I don't see that he's maybe muted. Yeah. James, your mic is muted. Can you please just unmute yourself? Let me funny. I wonder if it's not just for interesting sake for people. I see they giving us a warning level stage 6 from tonight. Load shedding.
Prof. Van Vieren, I think you should just call James then.
I'm just phoning him now to see if what is happening.
Joey, did you see that James wrote in the chat? Bertie, did you read it?
Yes, we did pick it up. We saw that he currently has load shedding in his area, so he cannot connect. So let's just see, James, are you completely off? Will it be impossible for you to share maybe just your PowerPoint slides, or is the connectivity very bad? If you can maybe give us an indication.
Hi, everybody. We've got a problem. James says that because of a power failure, the communication is not working with him. He says the power's only back at 12. Now I'm going to try to do a shift. Roxanne, is it possible that you can start earlier?
Yes, sure. I'm ready. Our load shedding is set to start at 12, but I've got UPSs going and everything, so that should be fine. Bertie also has a backup of my presentation should I go off the grid, but I don't mind at all.
Okay, so I'm going to introduce Dr. Roseanne Bailey, and then she's going to now present before Mr. Ramabu. Dr. Roseanne Bailey is a senior lecturer in computer science education at the Faculty of Education, Northwest University. In the old days, I was also there. It was then called Potchefstroom University. Our main research focus is the promotion of self-directed learning through the implementation of cooperative learning and blending learning, especially in the fields of computer science and education. She has received several research grants for her research and is currently involved in 3 research projects aimed at investigating technology-supported cooperative learning in computer science education modules. Roxanne was also selected as one of the 3 research fellows to complete a 4-month fellowship under the guidance of UNESCO Chair for Personalized and Adaptive Distance Learning. She has published her works on national and international levels, and she acts as a supervisor for postgraduate students. Apart from her research focus being implemented mostly in computer science education modules, Roxanne also investigated strategies for supporting novice programmers at high school level. In grade 10 as well as tertiary level BH students, where she does introduction to programming for them. Thank you very much, Roxanne, and thank you for your time that you are sharing with us, that you can present to us as well.
Thank you, and
I'm
thank you
giving
for
it
that.
over to you.
Thank you for that introduction, and thank you for the opportunity. Now, we are all very happy that we are computer literate, but oftentimes computers can, do whatever they want. So please do bear with me. I'm going to start my presentation. And I think we're also tired of this, can you see my screen question, but may I just ask, can you see my screen?
Yes, it's there, no problem.
Okay, thank you very much. So colleagues, yes, as was mentioned, I'm Roxanne Bailey, and I'm from Northwest University, and I've been there since the beginning. I started studying my B.Ed IT. I had a major in IT education in 2006 already, so that gives away my age. And just also a little bit of a background, specifically thinking about the fact that we are speaking about novice programming. I had computer science higher grade at high school level, and that was my first, let's say, introduction to programming was in grade 10. And luckily, that's also where my love for programming started. So that's also why I actually chose to then become an IT teacher. That's what I wanted to be. So with that being said, let's get going. So if I can ask you, if you have your cell phones with you, or your even if you rather feel like going on your browser, if you wouldn't mind, please going to Mentimeter. You can follow the link. I will try and put it in the chat. Let me see if I can do that. You go. You should be able to follow that link. Maybe let me just, for data's sake, I'm going to just switch off my camera just to make that a bit easier. So if you can go to the Mentimeter, that would be great. Bertie, maybe I can just ask you, I see we've got 6 people who have joined. Have you been able to join, Bertie?
Yes, I'm here.
To put you on the spot. Okay, 7. Maybe we can just wait till we have...
Can I just move back to the slide that has the QR code?
Thank you, Bertie. There's also the code. If you are on Mentimeter and it asks you for a code if you want to join a presentation, you can also just type in the code. That should also work.
Sorry, I missed it. What is the code?
It's 96. Let me share that instead of my presentation. You should be able to see that 9618127.
Roxanne, sorry, it's Suki. I would just want to tell you we are struggling to get into Menti. We've tried from the browser and the phone, so that might be the reason why some people are not joining.
Okay, I see we've got 27 people joined already. So maybe if you can just refresh your browsers. Suki, I know you know how to do this. So if you're struggling, I know it's not you, it's me. That old saying. We've got 29 now. Suki, any luck on your side?
Still waiting, but it's fine, Roxanne, as long as you know we are here.
Okay.
Good luck.
Right. We've got 31 people who have joined. So let's start. For those who have joined, I think we have enough people to actually be able to get going. So the question being, how did you first learn to program? Self-taught, resource-based teaching, so that means YouTube or textbooks or whatever, also being self-taught, but perhaps with a lecturer. And then I was taught by a lecturer or a teacher, saying that you relied heavily on them, not you didn't teach yourself at all. That's the difference between being self-taught and being taught by a lecturer. And then resource-based, of course, saying that if you're watching a YouTube video, then, and that might have been a lecturer teaching you via a resource, but you were actually engaging with that resource. Okay, I was taught by a lecturer, teacher, definitely taking the biggest chunk at the moment, self-taught being 8. And then resource-based, I'm going to just give 10 more seconds. Okay, next question. When faced with a new programming language, what's your feeling? You can just type in, it should give you an opportunity to just type in any word that you are feeling. I just want to actually see that we're just getting to know each other, to see how we are feeling. How do we view programming? Okay, excited. That is very good to know. Oh, scared. That's the general feeling I get from my students more. Intimidated, challenging, which is not necessarily negative. Overwhelmed. Interested. I think someone's mic might be open. I can hear myself. Reluctant, nervous, happy, enthusiastic, tired before you start. I presume that person might have been engaging with new programming languages more than once. Eager, syntax. Okay, so that person's thinking just syntax. Stressed. I'm just trying to see which ones are new. Anxiety, excited, eager. Okay, so overall, it seems that there is quite a positive feeling, although definitely a feeling of nerves and being challenged. So I just want to quickly get back to my presentation. Thank you for participating in that, colleagues, and we'll soon get to talk about that. So as I saw, and as most of you indicated, I was also taught programming. My first programming introduction at school level, as I was saying, was being taught to code by a teacher. So unfortunately, this was kind of how it felt, and I hope the video is going to work. So let's see.
Roxanne, you can just share with sound. When you do the presentation, just say share with sound.
Thank you, Bertie. Let me do that.
In 1930, the Republican-controlled House of Representatives, in an effort to alleviate the effects of the the Great Depression, passed the, anyone? A tariff bill, the Hawley-Smoot Tariff Act, which anyone raised or lowered? Raised tariffs in an effort to collect more revenue for the federal government. Did it work? Anyone? Anyone know the effect?
Ellie.
It did not work, and the United States sank deeper into the Great Depression. Today, we have a similar debate over this. Anyone know what this is, class? Anyone? Anyone? Anyone seen this before? The Laffer curve. Anyone know what this says? It says that at this point on the revenue curve, you will get exactly the same amount of revenue as at this point. This is very controversial. Does anyone know what Vice President Bush called this in 1980? Anyone? Something DOO economics. Voodoo economics.
Okay, so
in 1930, there.
As I'm sure a lot of us can attest, teachers, lecturers often really try to impart their programming knowledge to us through Q&A, as we saw in this video with Beulah. And I must say I love this video because I often go to the practical sessions with my students, and this is how it sometimes feels, just quite disconcerting. So, of course, there is a time and place for everything. However, relying solely on a lecturer demonstrating a piece of code and you blindly following really does not bear much fruit, we've realized. And in turn, it actually creates a lecturer-dependent student who, when faced with a new challenge or a different scenario, which often is even very similar to the scenario that we have gone through in the class, they don't have the ability to transfer their knowledge from one situation to another. And this is exactly the problems, colleagues, as to why we have decided to, not decided, but have been inclined to rather go towards skills-based learning, where we are trying to encourage our students to become self-directed and rather not just be content-based or syntax-based in that sense. Now, of course, I really don't want to make this presentation a theoretical overload of jargon. However, it is obviously important to just elucidate what definitions drive my understanding of the concepts pertaining to this presentation. So, of course, these scholars are quite old, or these references, so an academic will immediately say, oh, but those references are too old. But these people are really seen as the pioneers in self-directed learning. Knowles, for instance, is seen as the father of self-directed learning, and he defines it as a process where an individual assumes responsibility for their own learning, sets their own learning goals, gathers resources, and chooses appropriate learning strategies, and evaluates their progress, all of which can be done with or without the help of others. So, of course, that last little part really does imply that the lecturer has a space in a learner's self-directed learning process. It's not to say that it's not self-study, it's not individual study. And this is often something that happens, is people see self-directed learning as something that's self-study, which it really is not. So Gibbons says that a self-directed learner should be able to ask questions, find relevant information, analyze the situation, make thoughtful decisions, determine his or her own point of view, and then test if the point of view is correct. And I think if we think of even just that Paul Yo's steps of problem solving, you will immediately see that there's quite some relation to that. And this is, again, just one of the reasons why self-directed learning is viewed so relevant in especially computer science. And then in the case of my expertise, well, or lack thereof, I would say, my focus is computer programming, specifically Delphi, and then, of course, also spreadsheets with computer applications technology students. So if we look at active teaching and learning, these are strategies that really place the student at the center of the learning process. Now, Konopka and his colleagues noted that active teaching and learning aims to create an environment where the student can actively engage in their own learning process, and in doing so, develop higher order cognitive skills. So I think, Professor Lister, and I hope I'm not mistaking here, but would also agree that we really want to aim to get to the point where our students can eagerly and easily engage with the higher levels of Bloom. But if we are not giving them the opportunity to actually reach those levels, then we are really giving them a disservice. So if we look at some of the active teaching learning strategies found in literature, which have been used in computer science education, we see that, and let me just say that this is really by no means an exhaustive list. I mean, I only mentioned 4, but these are just some that popped up. So technology-assisted learning strategies, or some people will call it e-learning, technology-supported learning, online learning, blended learning. It goes by many names. But this has really been on the fore, especially now in the times of COVID. Then we see strategies like problem-based learning, and I think we tend to use this not perhaps as structured in our own computer science classes, but I think something like the PAT at high school level was perhaps intended to be a problem-based learning and semi-project-based learning activity. However, in my experience, and this is just really limited from my own views, it's really moved to something that has actually been taken back to a teacher-directed checklist and tell the learners exactly what they have to do exercise, which please, and I will be open to engage with, in some conversations about that, but it does not seem like that was the intent when it was initiated back in the day. So then, of course, peer instruction in various forms. And then one of the strategies on homegrown soil, which I think a lot of us have engaged with, is pair programming as a cooperative learning strategy developed by Prof. Elsa Mens and Professor Leila Goosen in 2008 already. Of course, Prof. Elsa Mens having written quite a lot on that when she was still very active in computer science education. So then, if I look at active teaching learning strategies that I use to attempt to at least promote self-directed learning in computer science education, I can just mention that I use 4 strategies, or I have been using these strategies in the past. And I can say that these strategies I've actually started using. I've been involved in, let's say, in computer science education since about 2010 when I was teaching IT and CAT, and then, of course, moved to tertiary and have just been using it furthermore. Also because of the fact just that if something works, why would you want to change that? So I just realized for me as a student, I remember that I really did not understand code. I really did not know why I had to memorize these chunks and then try and apply them to scenarios that didn't make sense. And it was only once I started engaging on my own and really being active with the content myself that I realized that this is actually something that I can understand. And then, of course, my programming excelled. And that was that process occurred in a cooperative learning environment. Prof. Elsa was the lecturer, and we did pair programming. And for the first time, I actually had the opportunity to really have to explain to my friend, why I'm doing some code the way I'm doing it, and why they are doing it the same way they're doing it. And really from that experience, I realized that there could be something to it. So obviously when I became a lecturer, it just made sense that I would continue to try and investigate this. So I will just briefly, and really, colleagues, I don't want it to be a, like I said, a too theoretical presentation. I really want it to be more practical and just share my experiences. So I'm just briefly going to go through these 4 strategies and as examples of what you could consider perhaps to promote self-directed learning. Now, pair programming as a strategy has been used in the industry, and I think we all know it's almost as old as time. However, it is a programming strategy that has been proven successful time and time and again. What lacked, however, was when one implemented it as a teaching learning strategy, was the fact that we saw, and not myself, but Prof. Elsa those years, saw that you still get the idea of one learner perhaps just running away with the code, especially the stronger learner, and the other one getting the marks and just free riding and actually not learning. So in that whole scenario, the idea came about to actually include the 5 elements of cooperative learning to ensure that both students are actually held accountable to learn and to actually engage in this learning process. So if we look at the 5 elements of cooperative learning, we see that we've got positive interdependence, and this is the element where the learners actually both know that we are sinking or swimming together. So if we both succeed, if one succeeds, then both of us will succeed. If one of us fails, then both of us will fail. So once you get that idea, you actually realize one student will know, I cannot let my partner fall behind because then I will also be affected. Then face-to-face promotive interaction, and this is the concept of actually having the student realize that I bring some resources and some knowledge to the table, and my friend does the same. And in this process, we are actually just expanding our resource base. Then individual accountability, and I think this is one of the elements that's really so important that's often not visible in normal group work, if I can say that, or even normal pair programming, is the fact that I still have an individual responsibility towards this group or this pair then. So I need to still prepare. I need to make sure I've got resources. I need to really take my role as the driver or the navigator seriously. And that's also why we still give them roles, is because then there's actually a specific responsibility given to that learner, and they know what is expected of them. Then, of course, social skills, which is not always the highest priority for programmers, if I may generalize. And I think often our students also struggle with that. And during this cooperative learning experience, then, even though it's pair programming in a sense, the students actually have the opportunity to develop these social skills, have conflict, work through the conflict, and especially even in our case where it's teaching students, they are pre-service teachers, this gives them an opportunity to really learn to work with different personalities, which is often not as easy. It's easier said than done. And then lastly, we have group processing, which really speaks to students being able to reflect and know what worked well and to transfer what they've actually learned from this experience or this learning process to the next one. So in my own classes, I used, just maybe I can just say pre-COVID, it was 2 students sitting together, 1 computer, the general pair programming way of doing it. Then COVID hit, of course, and I started thinking, how will I actually do this, online? Because I really didn't want to fall back to an individual teacher-directed way of doing this. So the first year of COVID, I used Google Meet and Google Apps. So the students would use Google Meet, and the driver would be the person running Delphi on their computer and then also sharing their screen. And then I asked the students, and they did find this frustrating, I will admit, that they needed to use the chat function to communicate, because I really wanted to be able to see that both students were really engaged, wanted to measure and make sure that they are actually taking the individual accountability serious, etc., etc. So unfortunately, in the face-to-face scenario of pair programming, I could switch the roles randomly and actually keep the students on their toes in that sense. But during the online, because the program was running on the initial driver screen, it was just impossible to, not impossible, but it would have just been way logistically, I think, challenging to try and actually switch the roles in an activity. So what I did do, though, is to actually switch the roles after an activity was completed, so that the students still knew that one would be a navigator once, and then they will have the opportunity to be a driver in the next session. So, and then the next year, our university adopted MS Teams, and I just moved over to MS Teams and placed them in pairs using the channel function, and they could go on, but it was pretty much the same situation. So anecdotally, and I did measure their self-direction pre and post this intervention, if I can say that, but that data is still being analyzed. So just anecdotally, I can say that I could see that the STL skills were promoted in the sense that the questions they were asking were higher order questions, the fact that they were actually engaging with resources, the fact that they were actually taking responsibility for their own learning. They weren't as lecturer dependent as what they perhaps would have been. And another thing that was really quite nice for me is the fact that when we came back to a face-to-face environment as this year, I just continued with this way. So in the class, I just said to them, bring headphones with mics, and they just continued using MS Teams. And this allowed that some students that actually had symptoms that weren't allowed to come to campus because of the symptoms of whatever reason, they weren't disadvantaged or isolated at all, because they could just connect to the class from their hostel room or from their flat or whatever. And then, of course, although COVID protocols or rules are somewhat lifted now, or mostly, I could at least also observe protocols as needed. So that really helped. And then a thing for me that really stood out was the fact that the students could engage with general computer skills, learning to use collaborative tools, learning to use some applications that they perhaps weren't needing to use before, as opposed to just opening Delphi and just being engaged with this one application in my classroom. So that I thought were quite nice advantages. Then as I mentioned, I also teach computer applications technology, and the module I actually am responsible for is the spreadsheets, or the introduction to spreadsheets. And although we might think it's quite an easy thing, I think Excel is an amazing software application. A lot of the students really struggle with it. They find it abstract. And I realized that, it's necessary to also try and develop their self-direction. If I just think of the time when we moved from, I think it was Microsoft Office 2010 to 2013, where it looked a bit different, the GUI changed. And some of my colleagues even were really so overwhelmed because they didn't know how to really, navigate through this. And that's really a place where if I'm a self-directed learner, I'll actually be able to gather resources, think critically, be creative, etc., and overcome this challenge quite easily. So that's something I really wanted to impart in my computer applications students as well. So I actually just went on with the pair programming, and you'll see there is quite a trend. I obviously love pair programming, and just took out the programming component. So it was more problem-based in the sense that the students got a problem to solve in Excel. And once again, there was the driver and the navigator, obviously the 5 elements of cooperative learning. And I used Google Apps. So they used Sheets, Slides, and Docs. And in this case, it was actually quite easy for them to swap roles, even in one activity, because it's such a collaborative tool. So I could just say to them, okay, after 10 or 15 minutes of engaging as a navigator, please switch and you become the driver and you become the one typing, etc. So here, once again, it was clear that STL skills were promoted, especially, once again, things like using resources and just thinking out of the box, etc. The online learning component was quite easy. So I had been implementing this in my class on a face-to-face and just experimenting with it while I was doing my face-to-face teaching and learning. And then COVID hit, and I think it was just by pure luck that I had been experimenting with this way of doing it in my class, and the students literally just went home, but they went on just as we did in class. Once again, of course, COVID protocols were observable, and I really did value the fact that general computer skills was also stimulated, which is such an added bonus when you are using more than just the application that was prescribed. Then, second, lastly, and this one is probably one of the strategies I was most excited about, was during my PhD thesis, I had the privilege of actually working with grade 10 IT learners, and I heard the question about whether they are seen as novice programmers. And yes, I was actually wondering, I don't know how I would answer it myself, but definitely that they struggle with programming often. I think we will not really have to debate too long. So I had about 23 schools in South Africa that engaged with my study, and some of them did pair programming without Socratic questioning, some did Socratic questioning on an individual basis, and some did a combination. And then, of course, just to be scientifically more sound, I did have a control group as well. But the group that outshined all the other groups was the pair programming with Socratic questions. So once again, we had the driver and the navigator situation, but the navigator was given some Socratic questions to help guide their questioning, because what I have found is that as we get older, we do sometimes know how to frame our questions better and think about things. But a 15, 16-year-old sometimes has a bit of a challenge to really know how to ask a question or what questions to ask. So the Socratic questions were really just a way of actually directing the questioning and really stimulating specifically critical thinking as a STL skill. As I mentioned, it can be implemented individually as well, and there were definitely some advantages to even just probing the questions to the learners, even when they were working individually. So I would really recommend, if you are not a fan of group work or pair programming for that matter, to still consider something like Socratic questioning, where the learner, once again, is placed at the center and given just some guidance as to how to direct their own thinking. So what did happen was that we found statistically that STL skills improved, critical thinking also improved. The students or the learners worked faster. I remember I had one teacher from I think she was from East London or something, and she was saying to me, you know what, you actually just made me more work. And I said to her, how did that work? She said, you know, they actually worked so much faster through the activities when they were doing pair programming that I had to think up new activities for them. And this is after this teacher was very reluctant to actually start using pair programming, because she said she thought it would actually take too much time, but it actually did not. And another comment was that from another teacher was saying that the learners that were the naughty ones in the class were actually now engaged because there was a structured way of them having to be engaged. So it wasn't just, once again, work with, you know, just quickly work with a partner. There were real specific strategies built in to make them more engaged in the learning process, if I can say it like that. So these questions are quite small, but it's just to show you what the questions entailed. So each student or each learner actually got a copy of these questions on I made a little keychain for each of them, and they could just flip through the questions. And it could be questions like the navigator could ask the driver, what would be an alternative, or what are the consequences of this assumption? You know, if we are using one structure, let's say repeat or whatever it might be, you know, what would be the consequences of that? How will it affect, and how can we actually apply this to everyday life? Isn't there perhaps a connection, you know? And it's through these questions that the transfer to the next scenario might be a little bit more doable or actually stimulated then. And then lastly, one of the more recent active learning strategies I've been using is what we call knowledge surveys. And this is something that's so simple and easy to use. So I often do this when I just really want the students to actually get to grips with what are we going to do in this lesson, what is expected of me, and how can I actually place myself in this learning process before we even start. So it's a tool to direct the learning process, and students know what they can expect in this lesson. So Carl Worth, one of our colleagues from America, is the guru in knowledge surveys. And what he has actually said is he realized that his students actually start learning how to assess themselves, because this is a tool that they actually also don't know. And this is also an SDL skill, is being able to reflect. And we often don't have this. And if you're not given the opportunity to develop this, where will you learn it? So just to give you an idea of how this knowledge survey works, it's really a self-assessment tool that the learner or the student then completes themselves. And you can use, I use my study unit outcomes, for instance. So a student can ask themselves, I can demonstrate knowledge and skills in using reiteration in a Delphi program. And then they rate themselves at the beginning, so that, and this is the post one, but the pre will look exactly the same. And they give themselves a rating. So, a lot of times all the outcomes will be a 0 or 1, because they might have heard of something, but they don't really know. And then, of course, the lesson occurs or the study unit is completed. And then they do the same survey at the end of the lesson, if I can call it that. And the idea is hopefully that they would have moved from a 0, 1 to perhaps a 2 or 3, or you can use whatever scale you want, up to 5 or 10 or whatever. But the point being is that the student gets the opportunity to really think, what have I learned? What progress has occurred? Where are still some gaps that I may experience, etc. And for me as a lecturer, this actually gives me an opportunity to see where are my students still, having some challenges. And I don't let this count any marks at all. So the students very easily or quickly realize they can be honest. It's not going to affect their marks because they are very mark driven. But at least it gives them an opportunity of knowing, okay, what are we going to do in the study unit? So it's just our outcomes and where have I progressed and where are my gaps? So it really stimulates their own critical thinking again, their reflection, etc. So Bertie, can I just, or Joe, just, in terms of time, I don't want to go over.
No, you've got some time still left.
Okay.
No problem.
So
if you come up until half past of the presentation, we can do some questions, and then Mr. Amabu can present. There's no problem.
Okay, no problem. Thank you very much. So just a short little clip on what some of my students said. We made a video on at our faculty with some lecturers that have been applying active teaching learning strategies specifically to promote self-directed learning. And you will see I do look a bit different than the photo on the program, but so sit back and enjoy.
Sorry, I don't have sound. Is there supposed to be sound?
I wonder why the sound is not working. Let me just make sure. Sorry about that. Thanks for giving the heads up. Okay.
gaan nie so lekker wees vir my nie, maar soos wat ons aangegaan het ons meer koöperatiewe werk gedoen. Ons het in pare gewerk waar ons probleme opgelos het en die voordeel daarvan is dat as julle 2 mense is wat saamwerk, dan kyk julle na 'n probleem uit 2 verskillende perspektiewe. So dit beteken julle kan meer oplossings kry wat dan sal werk vir die probleem.
It's really actually exciting because like you learn a lot from them, they learn a lot from you. You have someone that can listen to you, that understands you.
Soos al hoe meer ons ervaar het in hierdie semester, het dit vir my lekker geraak want jy sien wat sê die ander persoon en hoe redeneer hulle oor 'n saak. So jy sien hulle oogpunt en jy sien ook joune en dan as jy nog steeds nie verstaan nie, kan jy die dosent vra vir hulp. So jy leer by 3 verskillende mense.
Ek voel dit is my plig as dosent om nie net leerinhoude vir die studente oor te dra nie, maar werklik waar hulle holisties ontwikkel om sukses te behaal in ander klasse ook.
Ek dink ek het nou meer daai metode begin toepas op al my ander modules omdat ons so min tyd het wat ons klas het 'n mens nou meer tyd dat jy self by die huis moet werk.
Voorbereiding is belangrik want dan weet jy waar gaan die les en dan het jy reeds al 'n voorsprong. Na die tyd dan kan jy ook weer refleksie doen van wat jy gedoen het.
Ek sou graag wil hê dat meer dosente selfgerigte leer moet toepas in hulle klasse. Want dit stel leerders meer in staat om eie verantwoordelikheid te neem. So dit beteken leerders sal beter vaar ook in hulle akademiese werk as wat hulle net passief sit in die klas en die dosent dra al die inhoud oor van hulle.
So I would recommend for lecturers to bring about group work in their classes and yeah.
CAT-221 het my definitief daai vermoë aangeleer om self te kan werk.
Ek voel
So yes, colleagues, as you can see from the mouths of babes, as they say, the students really, although starting to be quite reluctant in terms of working in groups, in pairs, they definitely do experience the value of it at the end of the day. I have initially, I can say right in the start when I was still very young and ignorant, I was very, very strict on the students had to work in pairs, etc. And they had to work in a group. And I have slacked and realized that students also, it's a bit of an overload for them to be in a social environment constantly in the class. So there are times when individual work is really also needed and, you know, students just needing the opportunity to focus on themselves, etc. So just to say, I do realize that group work is good, pair programming is good, but I do also advocate for the fact that sometimes giving a student an opportunity to be an individual is not always the worst. So just a final thought, if we can go to Mentimeter again, just to wrap up, and then, yeah, I'll almost be done. Okay, so what skills do we need to be a successful programmer? That's the question. I presume we're all still connecting because I see there's no one connected yet. Oh, logical thinking. Okay, thanks for that. Problem solving. Reasoning, interpreting. Tracing. I wonder if there's a link to that word and Prof. Lister's talk earlier this morning. Dedication, patience, definitely patience, perseverance, creative thinking, computational thinking. I don't see anyone saying knowing syntax or memorizing code or anything in that regard. And this is what I was hoping to get at, is the fact that once we move away from this idea of memorizing code and chunks of just code structures and moving towards a skill where a learner will be able to actually just transfer whatever knowledge they've got into different scenarios, then that they would actually have success in program. So I see patience, dedication, good lecturer. Yes, that's an interesting one, a good lecturer. My question always being, if you have a good lecturer now and you end up having to code in another language and that lecturer is not there anymore, what will be the situation then for you? Thanks for participating in that. I'm just going to go back to the PowerPoint just to finish off. Okay, so if we look at self-directed learning skills and characteristics, it includes characteristics like, or skills like perseverance, creativity, being resilient, being self-motivated, having a love for learning, being inquisitive, questioning assumptions. You know, I think we can, or a lot of us can attest to our good programmers in our classes are often the ones that challenge us as well. And that's because they actually have the skill. Goal-directed, critical thinkers, problem solvers, being reflective, and obviously having 21st century skills. And if we look at the responses we got from the Mentimeter, it's definitely clear that there's a relation between a good programmer, what we as a collective see as a good programmer or programming skills, and self-directed learning skills. Then, of course, just to bring it to our education and specifically our basic education, if we look at our general aims in the CAPS, it's clear that it totally speaks to a self-directed learner. It's someone that can identify and solve problems, cooperate effectively, analyze, organize information, communicate, apply, you know. So if we once again think of the definition of a self-directed learner, and you look at these aspects that are mentioned by the department, it's also clear again to see that we are supposed to really be developing our learners to be self-directed and not just know code. So, of course, our students and learners need self-directed learning skills to be successful in computer science and especially in programming, especially because we know programming is such a dynamic field that really changes. Programming languages change, problems change, scenarios change, etc. It is our responsibility to ensure a conducive environment that will stimulate these skills. And there are many, many active teaching learning strategies that you can use. And I would suggest one experiments with them as much as you can and really see what resonates with your personality, what you can deal with, and what you feel comfortable with, because it's definitely not a one-size-fits-all recipe. Thank you very much. There is my email address as well, and just to say there are the references. Thank you, Chair.
Thank you.
Thanks so much. Sorry, Betty, you can go on.
I just wanted to say thank you, Dr. Bailey. It was quite informative, and I think we can all learn from that approach where we kind of have champions, and Prof. Lister also alluded to that in his first kind of a talk when he said that you can have a class champion that assists others, and I think that is one big approach that we can all learn from and adjust our own teaching strategies to also include these kind of approaches where the students assist one another and help one another to master the content. I do not know if there's any questions. If there's somebody with a question, they're more than welcome.
I've got one question, Bertie. The question is, during load shedding, yes, you've had this pair programming model. Did you find that students are not that active since COVID that they were before COVID?
I actually did, definitely let me say this, my contact sessions that I had scheduled, where I said the students can connect and ask me questions, that they were definitely not as engaged with. Few of them would actually attend the contact sessions. What I was really glad about and thankful for was the fact that the activities I was giving them were that they had to do, I gave them the partner that they had to work with in that week. And then, like I said, I asked them to use the chat function so that I could kind of make a sense of the process the pair went through, so that they engaged with quite actively. I think it was an assignment, and obviously they knew that I was going to mark it, and it was going to count towards their module mark. So they definitely still engaged with each other without and also perhaps I can also just say this. Pre-COVID, students had to come to the class and it was synchronous cooperative learning or pair programming, if I can say that. And then when COVID hit, I had a bit of a mind shift and decided to allow them to actually work on an asynchronous way as well and work on a time that really suited them. So I did ask the students to try and really negotiate with each other in terms of diaries and what worked for them. And I think that actually made them be more engaged because they could feel a little bit more in control of their time, as opposed to always coming to my class at a specific time. That perhaps, for some students early in the morning is really a challenge. So, I actually think they were more engaged in that sense.
Thank you. I just want to ask if there's still people that wants to ask questions. I didn't see anything more in the chat box. If I just want to ask if there's somebody else that also wants to a question. Bertie, did you receive any other questions from your side?
I did
Okay,
receive
you can go on.
Yes. It asked, Dr. Bailey, the schools that you visited, was one in a rural area with lower kind of resources, and what did you experience if you did visit such a school? Is there any experiences that you have that you could share that was different, or was it also motivating?
Yes, so the 23 schools, I actually initially started with 25, but 2 fell out or withdrew or whatever. And they were really equally spread in terms of, I actually stratified in my grouping to make sure that I had schools in urban areas or metropolitan areas and then rural areas. So to give you an idea, and I think my colleagues from Northwest will know, but one of the schools, you literally drove past the cows and the dirt road, my poor little car really, really just managed. But what actually helped was, thankfully, that school was a pair programming school. And the fact was that they didn't have enough resources, but because the learners were working together on one computer, it obviously halved the resources needed in terms of computers and textbooks, because you should know the navigator really is the only one that's allowed, if you want to say that, to use the textbook just to make sure that they feel I've got a role and I've got a role to play here as well. And the driver is the only one using the computer so that they feel this is my work, this is my job. So luckily that teacher, he was letting the students work together on computers, but in an unstructured way. So what would happen is, you would get the overbearing student that would just hog the computer and the other one probably fell behind. But with a more structured way of working in terms of saying to the teacher, give them specific roles, swap so that you make sure that, the students or the learners actually both get an equal opportunity in front of the computer and with the textbook, really did help. So I actually think it's an answer for the class with less resources, even more so than the class with a lot of resources. I hope, yes, I hope that answers the question.
No, it did indeed. We have some comments in the chat which says, thank Doctor, it's really inspirational and that a big reminder that I as a teacher should adjust my own teaching habits again. So that was just a comment that was made. Then we also had somebody asking about the recordings. What's going to happen is we've got a person dedicated at TUT that's also joined us here, and we spoke about him this morning. He's going to edit the recordings for us, and then we will make it available at a later stage. All the live streams are available on TUT's Facebook page, TUT Live, so that is available there, but we will also release a nice set of edited videos that will be available for everybody, and we will communicate that at a later stage. So from my side, we would like to really thank Dr. Roxanne. Prof. Van Vuuren, maybe you want just to close?
Yes, thank you, Dr. Bertie. I just want to say why we say edited. You know, there's a lot of times that we break for 10 minutes and 5 minutes, then it's dead time on the video. So we don't want to have the videos that long. We editing things out that that is not necessary to be into the videos. But thank you very, very much, Dr. Bailey. We really appreciate your presentation, and we really enjoyed your presentation very, very much. There's one thing that I also want to congratulate your students, that they're so active and that they prepare for lectures. I think that's the one thing that we from TUT must learn from you. How would we get our students also to prepare for a lecture? Because it seems to me that is a really good thing. I don't know how many universities the students will prepare for a lecture.
Perhaps
So
I can
maybe
just
you
jump in there. I just want to say, I think that's the value of having them work in pairs, is the fact that I can't hide.
Yeah. We lost you. You said can't hide. Oh, I think we lost Dr. Bailey just now.
I'm back, revived from the grave. Yes, so I think the fact is just I give them partners, so it's not friends, and that's also one of the reasons why I actually rather divide them myself, because if it's my friend, then they will think, oh, it's okay, I know we had, you know, a visit last night and you couldn't prepare for the class. But if it's not a friend, it's a bit of a bigger embarrassment if I get to the class unprepared and you prepared. And now, you know, I'm looking like the person that's really failing the pair. So I think that helps as well. And that's also one of the advantages.
But thank you very much. We really, really enjoyed it, and we will definitely try this approach as well, especially now in these times that we need to get the students to work on their own and do self-directed learning, because at this stage it is quite a difficulty, because from our side, if I might add, what we found is that students come from schooling systems that they get directed learning all the time. They instructed by teachers and they only do that, and then it is a real difference for them to change to self-directed learning. But we've learned quite a lot from you, and we will definitely try that methodology to get them to learn themselves. Thank you very much for your time. But please stay, and if I can, you can also stay for the rest of the day as well as tomorrow. I hope you also find it very interesting. I just want to check, Mr. Amabu. Can I just get the indication if your load sharing is fine, if you can start now?
Yeah, it's fine, Prof.
Okay, so but I'll just give a 5-minute break, but everybody can just do a 5-minute break, and then Mr. Ramabu will be ready to start after the 5-minute break. Okay, so that means we will start at 12:40. Good afternoon, everybody. I hope you're all back into the room again and that we can continue with our webinar. We're so glad for this opportunity to work with everybody in the webinar and to see all the faces that's joining us that we never saw before. Everything, we're so glad. We want to now welcome Mr. James Ramabu. As previously said, he studied until master's level at UT, and he is doing his research in computer education, computer programming education, and he has got a very nice program that he's using for actively engaging students for programming. I'm very sure the teachers and everybody will be very, very interested in this program that you started to implement. Thank you. I'm giving it over to Mr. Ramabu. Just again, for people that are connected late, please put your questions in the chat box and we will do it, the questions afterwards. Otherwise, you can email the questions to Bertie and he will get the questions that you can do it anonymous and he will ask the questions afterwards.
Okay,
thanks,
thank
Mr. Ramabu. You can start.
Thank you, Prof. Joey, and the organizers of this workshop. I think so far it was worthwhile. I learned a lot personally. Thank you, Prof. Lister. I always read your work and it was an honor today to see your face. Thank you very much, and all the speakers. I'm going to share my presentation now. Yeah. Okay. As indicated, my name is James Ramabu. I work for the Department of Computer Science at Tshwane University of Technology. Currently, I'm doing a PhD with the University of South Africa within the area of programming education. I started doing this qualification with them since 2017, and then we're still continuing. I've been active in the area of programming education in terms of both teaching and research. So in 2018, what happened is that I started to have interest in teaching programming using physical objects, or you can refer to that as manipulatives. Firstly, I wanted to know if there are people who are using these manipulatives. And then I have to ask this question to Special Interest Group on Computer Science Education. I'm a member of SIC CSE. I'm sure that some of you are members as well. Special Interest Group on Computer Science Education is a subgroup of ACM, focusing on computer science education. So for us to see if educators are using physical manipulatives or any other objects to teach programming or assist them teaching programming, we posted this question in the mailing list. If anyone has tried using manipulatives in teaching programming concepts, or know of anyone else who has, could they please email? And then that was my email address, and that was posted in February 2019. It was interesting that we found educators making use of many tools, many objects that do not have a link to computer science, but they help students understand some of the concept. Let me just share with you the report that I got from the group. This is the summary of what I received. I compiled, I think I got 21 responses from a special interest group on computer science education. And then some of them suggested Russian dolls. I think this was used for teaching recursive functions. Some of them suggested the use of the deck of cards for teaching arrays and linked lists. And then some of them used the students as manipulatives to emphasize sorting. What was interesting again was, where is that one? Yes, the use of caps, the use of two classes to indicate that the two numbers are swapping, or whatever that is inside those variables can swap. So this person made use of the classes and the third class to indicate swapping. If you want this document, you can email me, I can share it with you. All these responses, they were not edited. I copied them as they were sent to me by a special interest group on computer science education members. And this is what they did. This is what they used to teach programming, introductory programming. This is what they used to emphasize some of the concepts in the introductory programming. Okay, so after I have noted that the majority of computer science educators used this object to teach programming, I tried it out myself through using CAPS. If I can go back to my presentation again. Great. And then what happened is that I wanted to make use of CAPS just to test if this thing is working. I had this question posted to students, and then it says if X is 8, Y is 10, T is 15, what is the value of X and Y after the execution of the given code below? T is equal to X, Y is equal to Y, Y is equal to T. And this question was given to students who were already introduced to programming. So I think they were somewhere they were busy with decisions and loops, and we came with these questions to test if they really understood the introductory concept of program execution. And then what was interesting is that 12 out of 30 students indicated that the value of Y is 15. And then when you check why they said so is because here you see Y is equal to T, And then what is the value of t here? The value of t is no more 15 because it was overwritten by the first line there, which is t is equal to x. But 12 out of 30 students indicated that the value of y is 15. So I think this traces back to what Prof. Raymond Lister said about tracing. They cannot trace back and say that the value of t changed. And now when the value of y has to be with the new value of t here, the new value of t has to be copied inside y. Okay, so I had a colleague, we had 30 students, and then we divided them into two. I have a colleague who taught the other 15 students in the other class, and then I remained with 15 students. So in my experimental class, I taught them, or I did correction with them using this experiment of cups. And my colleagues on the other side, they did not make use of these manipulatives. So this cup will represent variable x, this cup will represent variable y, this cup variable t, and those papers with numbers in the cups, they represent the values in the variables. So as when I explained t is equal to x, I had to look for another paper and write and copy the value of x and then put it inside the cup, the teacup, and remove whatever paper that is inside the tea and throw it away, which is the demonstration of overwriting. It is replacing the old value until we come to a point where we demonstrate y is equal to t. And the response was, oh, okay, that's how it works. And I think that's a good feedback as an introductory programming teacher. When you teach and you hear this kind of feedback, you must know that at least you are doing something right. The student understand what you are doing. Whatever method of teaching you are using is working, because when you get feedback, it validates the method of teaching you are using. So as time goes, I think it was in 2020, COVID-19 happened. And then the main focus was that I wanted to experiment many physical objects. I had to look for the decision statement and look for the appropriate physical object to demonstrate decisions. I had to look for loops and demonstrate again, and then the arrays. But COVID-19 happened. That's where we shifted away from physical manipulatives and moved to visual. Actually, at that time, I called it visual manipulatives, where I started to design something similar to physical manipulatives in the form of a program or a program animation. Okay, firstly, we had something like this. Okay, let's read this question. I will show you how I demonstrated this in the next slide. What will be the value of k and t after the following program code has compiled into k, t, case 1, case 2, k is equal to t. So with a little program that we designed, we had the code in this list box, and then we had a variable k, which is something like a cup, the demonstration of cups, and then variable t, it looks like a container. And in this case, what happens is that when I hit that run button, that blue highlight will start from int kt. When it hit that line, these cups will appear. At first, these cups or containers don't appear until the blue highlights come there. And then when it hits k is equal to 1, and then you'll see that the values 1 will appear inside here, will float from top to bottom until it reaches where the container is. The same applies to when the blue highlights comes to t is equal to 2. 2 will float from top to the bottom and land inside that container, which indicates that variable t now has 2 inside. And then we have k is equal to 2. K is equal to t. In this case, what happens is that the copy of t, variable t, will come out, go up, go all the way and land inside the variable k there. I think let me just demonstrate this with the actual app so that you can see what is happening. Yes, I believe that we're able to do this. By the way, I developed this using C++ or Embarcadero. So when I click that, the blue highlights there, and then 1 comes, and then there's a 2k is equal to t, and then you see that the copy comes and go and replace whatever that is inside the container of k. And then the student should be able to see that the value of k is not added, because the other misconception that we noted from the student is that k is equal to t. They thought that the value of t will be added inside whatever that is inside k, so meaning that it's going to increment whatever that is inside there. So at the end, they thought k is equal to 3, because we did the post-test and pre-test exercises before we demonstrate this. In the same way, we divided the student into control group and experimental group and see what did they think of the answers before we demonstrate this app. And we compared 2 groups, the group that were demonstrated with this application in the group that did not have this kind of demonstration. Okay, let me go back to my presentation. Great. Okay, this is just a demonstration of the same thing. Great. And then we moved to decisions because now we were fully in the area of animation-based solution. We moved away from the use of physical manipulatives. They worked. I have to say that the use of physical manipulatives works, but because of COVID-19, we were not able to continue in that area. And then we also found that this is more compatible to online delivery as well. And then when we check the other method, the physical manipulative, it was going to be incompatible with online delivery. So this animation program here is about introducing decisions, nested decisions. So what happened, the other misconception that we found here is that students did not understand how nested statement, if statement work. We gave them a program. We divided them into control and experimental group randomly and gave them the exercise. I will show you the exercise. The post-test exercise and the pre-test exercise to see what they knew before our intervention. And then what we found is that a solution that needed a nested statement, student made use of pieces of if statements which were not nesting, which was a problem because we have problems that need a solution in the form of separate if statements, and we have problems that need a solution in the form of a nested if statement. So in order to treat that, we came up with this animation program where firstly, we have to start from the basics before we get to advanced stuff. I think that's what Prof. Raymond Lister emphasized. Sometimes we neglect these basics and jump to advanced stuff like nested decisions, nested loops, compound statements without emphasizing the basics. So with the simple if statement, what happens is that when that button, the process button is hit, we have an input box there which represents the value that is going to be stored inside the number. And note the arrow on the left there. When it points to the C-in number there, and then you have to enter a number. So in this case, what happens is that 5 is less than 10. Therefore, it's going to demonstrate that number less than 10 will be displayed. And then the yellow square there will flicker several times, which indicates that the if condition is being evaluated, I think for a few seconds. Okay, so firstly, after the user enter 5 and press OK, this is a progress bar. The progress bar will start to move from top to bottom, changing the color from green to gray. When it reaches that yellow square, the yellow square will flicker several times, few seconds, and then it means that the arrow will be there at the if. Okay, I think here it shows what I'm talking about. If that arrow is at the if clause there, this yellow square will flicker several times, indicating that, okay, I'm thinking the condition is being evaluated. Okay, and then when it's done, if the condition is true, then the green color will gradually decreases until it reaches that box C out number less than 10, and the gray color will take over. And then at the end, the student will see that, okay, if the number is less than 10, this is displayed. If the number is not less than 10, then this green bar will remain green, meaning that this code is not touched, it's not executed. Okay, so, and this is what happened. 5 less than 10, and then the code has been executed, and this is the output, number less than 10, and then complete. So what we emphasized again is that this C out complete will execute because it is not under the if clause there. So the execution of this line doesn't depend on the outcome of this if clause. And then we got good feedback when we demonstrated this. Some students understood the use of decisions from the beginning. Okay, so as we continued, we wanted to do something more with the students. So we thought of coming up with a scenario that will include the whole nested statement and the short circuit operator and an OR so that student can understand the overall concept of nested decisions and when to use it and how it works. Okay, so if we can just read this scenario so that we can understand what will happen in the next slide. And we read this scenario with the students several times until they understand it before we move to the solution and how we model the solution with the animation program. It says you are requested to write an algorithm that shows the process for an employee to get an access into the office. An employee has to go through a gate authentication, then finally go through office door authentication. At the gate, you need to use a gate access card or identity document to get in. If you get access, then the next stage you need to use both office access card and office door PIN code for the office to open. To demonstrate how the authentication from the gate to the office will work, follow the instruction below to complete the algorithm. Okay, prompt the user to enter Y for N, Y or N for the gate access. Y means yes, N means no, Y and N for identity document. If the gate card or identity document contains the value Y, then proceed by prompting the user to enter the letter YN. Otherwise, show a message access into the company not granted. So the same thing, Y for yes and for no. Check if both office door cards and office door PIN contain Y. If so, show a message access into the office granted. Otherwise, show a message access into the office not granted. So what we wanted to achieve here is that the student should be able to understand that when this employee get to the gate, before the employee can reach the office, at the gate they need either a gate access card or identity document, one of them, not both, one of them. And then when this employee get to the office, two things are needed and it's compulsory for them, for those things to be provided: office access card and the office PIN code. So for this employee to get access into the office, those two things are compulsory. And at the gate, only one of those things are needed. Okay, so we modeled the solution by providing something like a flowchart, but this one is interactive. Well, firstly, we had a code. We explained the code. Before we ran the animation, we explained the code, how we came up with this code so that student can understand. And we know that always will have students who don't understand. And even if you say ask questions if you don't understand, they won't ask questions. Maybe they're afraid of asking the questions. So this animation really helped a whole lot of them, because after demonstrating, we got a similar response of saying, oh, okay, oh, that's how it works. That's how it works. And that's a good feedback as you are teaching. It encourages you that, okay, as a teacher, I'm doing something right for this student. I'm helping those who are struggling. Okay, so we explained this code, how it works and how the whole thing, the if statement, what is the purpose of this sign or sign in the end, and before we demonstrated it. And then with the demonstration, I'm going to demonstrate it again, but let me just explain it here. Gate access N, I use the input box here in the form of CIN. So CIN gate cut is N, and then when the blue highlight moves to the next line, it will request for ID cut, and then N, it means no. And then on the evaluation, again, the yellow square will flicker several times it will indicate that, okay, I'm busy processing the conditional evaluation here. It should either be true or false. And then corresponding text there, which is helping the student, false or false, because we entered N and N. And then at the end, we'll say that, okay, access into the company not granted, because the person did not have the gate card. At the same time, the person did not have identity document. And then we know that it's false or false, which is equal to false. Okay. And then the next demonstration, in case you have either gate card or identity document, the flow will take the true direction, meaning that the gray bar will gradually move from right to left. The green bar and the grayish will grow until it prompts the user to enter the office card there, which is no. And then once it's no, it automatically takes the false side, because no and yes will be no. Okay. I think, let me just demonstrate how it works so that you can see what is happening. There is okay, so let's take the slider. Okay. Okay, firstly, it will move like that. I believe we're able to see my screen. And then have gate cut. I will press N, which is for no. Then I press OK. And then have ID cut, no. And then I'll press OK. And then the blue highlight will move to the conditional point, and then the flickering will happen, which will give the student time to understand that the condition is being evaluated. And again, the student should be able to see that the whole code between this brace and that brace is jumped, is totally jumped, because the blue highlight from here jumps straight to the else part. And then access into the company not granted. If I can just reset and start again with different values. So in this case, what happens is that let's put Y and N. Okay, and then the blue highlight reaches the conditional point. The thinking is happening to evaluate either to true or false, and then is taking the true side. So I will have Y for yes, yes, there is an office card, and then I will have no, and then press yes, and then when it reaches the if clause there, the thinking is happening. That flickering means that, okay, I'm thinking, okay, I found it is true or false, which is called false. Therefore, access into the office not granted. Okay, the last demonstration. So I will have, let's just have Y and Y here. Okay, and then it will take the true sides. So in this case, I'm going to use Y and Y. And then again, when it gets to the yellow square, it will flicker, indicating that, okay, I'm thinking about this condition. And then the results are there, true and true, which is true. Access into the office granted. So at the end of the day, they should be able to understand that, okay, this chunk of code will never ever be executed if this evaluation is false. Okay, and then let me close and return to my slide. Great. Okay, this is just one of the animation programs I developed. I have several of them, but I just wanted to demonstrate this one only. I have the one for demonstrating the use of functions. I have the one for demonstrating nesting loops, the one for arrays as well. And then I think the student appreciated the way they understand the whole thing because of this animation program. And the feedback that I received as I demonstrate this was really interesting, because in the past, as I was teaching this kind of stuff, I didn't get that kind of feedback, that kind of response. Oh, okay, that's how it works. This is really cool. I now understand. See. And then again, another thing which is very important is, we have many tools, existing tools in the literature. Some of them, you find them in the internet for free, but they don't have guidelines. There is no pedagogy that comes with that particular tool. And sometimes we tend to take them and use them and use them the way we think they will be appropriate. And at the end, you may find that you are doing more harm than good. Whatever tool you think is working is not actually working, is actually introducing more confusion into students. So this animation program, they come with guidelines, working guidelines that we have tested. And some of them, we are still documenting them based on our experience of using these animation programs, because they're important. Guidelines of using these animation programs are very, very important. If you just take this and demonstrate without understanding the recommendations of the researchers, it might not work for you. Okay. So on that note, thank you very much. Comments and questions, if they are there.
Thank you very much, James. I didn't see any questions in the chats. Bertie, did you receive questions from your side?
Yes, there was a comment in the chat. It asked, did you ever investigate Flowgorithm and how it works? It's a very useful tool. You create a flow chart and you can see the memory contents as it changes. You can also view it as the algorithm in any programming language or pseudocode. So that's something to be investigated. It was just a comment. And then Prof. Lister said, nice work, James. And I think, James, we're coming from the same background, know that we need to do every effort for our students to be able to understand the concepts, and what you're doing is nice. And I think we're all working towards creating students that's valuable and that has mastered the problem-solving skills, especially for our novice problem solvers and our novice students that's exposed to programming for the first time. So I would really like to thank you, James. And that was all questions. There was also another question, is the tool available for use and how can we access it? James, if you maybe want to answer that question.
The tool is not yet ready because we are still, it is still a prototype, and then I think it will be ready once I'm done with the qualification, because we're still finalizing the tool.
Yes, okay, so I think that would answer. And somebody else, James, did you develop the animation yourself?
Yes, I did it myself.
Right, and then there's another hand up of Nkosikona Dlamini.
You can speak, Dlamini.
Hi, colleagues. Thank you for the opportunity. I just want to check how are these tools evaluated, and when they are evaluated, how are they checked? So this would probably be, if it studies, it's gonna be your findings maybe, or your experiments. What exactly do you do when you say, okay, this tool is great, or this tool needs improvement? So the evaluation is based on what matrix?
Okay. Firstly, when I designed these tools, I followed cognitive load on multimedia learning theory. So that, you see, when you are developing a multimedia learning material, there are certain steps you have to follow. Then I followed that process in multimedia, cognitive load on multimedia learning. And then secondly, when we test this, we divided the students into two, control group and experimental group, randomly so. And then the control group, we gave them a pre-test algorithm, which is the same in control group and experimental group. And then when they are done, we divided them. The other group in the control, they had another lecturer, head colleague who assist me. They did correction without the assist of this tool. And then on the other side, I did correction with this tool. So at the end, we had another algorithm, a post-test algorithm, to check what happened between, did the tool have an impact or not. That's where we did our comparison, and that's where evaluation happened. And we didn't do it once. I think we've been doing it several semesters. At the end, because we are following a practical action research methodology, at the end of a semester, we look at the tool and reflect and see where we can improve. And then the next version get improved, and we demonstrate again, we test again if there is a need to do it again. I don't know if I answered you.
Thank you.
There was
some more questions, Bertie.
Yes. The question reads, over and above the response from the student, did you see some changes in their marks?
Yes. The post-test, both pre-test algorithm and post-test algorithm, we graded them, meaning that we marked them, we gave either 1 or 2, there is a rubric. And then as we compared the result, we found a good progression, learning progression, based on the pre-test and the post-test as compared to the progression in the control group, meaning that there was significant improvement with the student. And by the way, when we invited the students to come to this kind of a session, we indicated that we are targeting struggling introductory programming students, those who are really struggling. And then another thing that happened is that there were students who came to this kind of sessions, but they were not struggling. But because we have a pre-test and post-test algorithms, we were able to trace those students, because at the end, you find that the student got, if the algorithm is out of 10, he got 10 out of 10 in the pre-test, and then the post-test, the student got 10 out of 10, meaning that there were no intervention necessary for that particular student. So at the end, we scratched them out because those who needed this, we see them in the pretest that, oh, okay, this student is not able to do this and this and this. But after the intervention, the student was able to do this and this and this. This one was able to do it in the pretest, and even after in the post-test, the student was able to do it, meaning that this tool didn't work. I mean, we got it from the beginning, and the same applied to the control group.
There's another question.
Yes, the question reads, will it be possible for somebody to add their own code to your application and then have the code animated?
So no, at this stage, the application doesn't allow a new code because this one was for teaching purposes, was for emphasizing certain things. So we did not have, the program doesn't allow a new code with the new animation. Perhaps we can look into that in the future. But this one was the main purpose, or the main focus was for the teacher to use it for teaching purposes. I think that one will work in the future, but it will focus on the student. The student will have to put a code and it will produce a corresponding animation from time to time as the student practice, something like that.
Thank you, James. We have another hand up from a person. You can put on your mic.
Keith, you can talk.
Hi there. Everybody hear me okay there?
Yes.
Okay, great. I'm really excited by seeing this type of thing. Just to bring context, I'm at a high school and I'm teaching from grade 8 right through to grade 12. And it's so evident that when we use these physical interventions, be it at the program level that we're looking at now or the CUPs or wherever it is, it really does empower the students, because as you say, there are some students who get it straight away and they can almost jump from the problem solving to the coding almost transparently, and it seems you one step. But I'll give you an example. I'm trying to work backwards in the sense of trying to make things more concrete and trying to move from the concrete to the abstract. And particularly at the lower the level you get, the more important it is, but it's important across all the levels. So, for example, the other day I had my kids sorting themselves in an order of height, which was essentially a sorting algorithm, but you don't tell them that. Okay, and they automatically devise structures, and you can see them starting to debate with one another, which is the better way to do it. And then you start to analyze it and say, well, okay, that worked for 10 people. What happens if we had to do the whole grade, for example, or something like that? And that just extends it. And it's amazing how they actually intuitively come up with the solutions or and even the efficiency that they look at. So I don't think we must ever underestimate the importance of the physical examples, because if the pupils can see a need for a solution and how the solution works, it just makes the workload and they go into it with such a more positive attitude as well. Thank you.
Okay, thank you, Keith. I think I agree with you. In our case, I did indicate that the physical solution is good, is recommended. But when we moved to online delivery, we found this animation-based more compatible, and also is also compatible to face-to-face delivery. Noted. Thank you.
Thank you. I didn't see another question. Bertie, do you have another question with you via the emails?
No, I didn't receive any, and I just checked now. So I think that concludes the questions.
Thank you very much, James. I also think the teachers are very excited. I think this is a real opportunity to get this program finished and distributed to the teachers for use in the schools as well as the novice programming in other places. I really think this is an exciting project that you're actually doing, especially for our people that mostly have children coming from school without any ID, in most times not CAT at all, and it is really helping our students to start thinking correctly and do problem solving. Thank you very much for your presentation. We really appreciate it. Then that is the end of today's proceedings. I hope you enjoyed today's proceedings. We will see you tomorrow morning at 9 o'clock when we start again with Prof. Lister. And remember, tomorrow we're going to do examples of question papers and see on the levels of Bloom's taxonomy, and that he comments on the Bloom's taxonomy from that side. And we will definitely ensure that we get the practical examples. And tomorrow we also got a teacher that is going to talk to us, that is going to talk about his experience from a township school, how to do IT in a township school. So thank you very much for your time today. I hope you've learned a lot, like I've learned a lot. And we hope to see you all tomorrow. Thank you very much. Bye-bye.
Bye-bye. There's a question regarding if there's another form. It's not necessary for today. We decided to combine it into one for tomorrow because we're going to treat it as one kind of session. And we would just like to thank everybody for their great inputs, the nice questions that was asked, and thank to all our presenters from the bottom of our heart. We really learned quite a lot from you, and it's informative. And this morning, as it's cold in winter here, I didn't even mind because I could sit and I knew that I'm going to learn something valuable. Thank you, ladies and gentlemen. Have a blessed afternoon. We're going to see each other then again tomorrow, just before 9 o'clock, and Prof. Lister the same time as today. Thanks, everybody. Thanks, Chris. Thanks, Prof. van Vieren. Thanks, James, and to all our other presenters. Roxanne, we really appreciate it. Have a blessed afternoon.